students, welcome to my YouTube channel Easy Mathematics. This video is about the graph coloring, which is one of the most important topic or important chapter on graph theory. So graph coloring, it have an immense use in the practical applications also. Graph coloring is a special case of graph labeling. Graph coloring can be possible with respect to adjacent vertices or adjacent edges or adjacent faces. The different type of graph coloring now described below. So the first one is the vertex coloring. What is vertex coloring? So a vertex coloring or simply coloring of a graph G is an assignment of colors to the vertices of the graph G such that no two adjacent vertices share the same color. Just remember, we are going to color a graph, in fact graph vertices here in such a manner so that no two adjacent vertices have the same color. So for observation, let this one is the given graph. For this graph, if we consider the total 5 vertices are given and let B1 is given as the color red. Now its adjacent vertices are B2, B3 and B5. So I'm just giving here the series also. So B1, it is adjacent to B2, B3 and B5. So B2 should be given another color. We can give B5 is also the same color and B3 also we can give the same color blue here. But B3 is again adjacent to B2 and B5 both. B2 having the color blue, B5 having the color blue. So B3 never can have the color blue. So that it should have a different color than blue. In fact, it is having a different color than red even because these two are the adjacent. So that we put it as the green color. So now after that this vertex is left. So this vertex is adjacent to this one and adjacent to this one. Here it is the yellow and this is the blue. But this vertex is not adjacent to B1 anyways. B1 having the color red. So that we can put this vertex the color red even. So that according to that we can say that in this graph we require total 1, 2 and 3 different colors to color. So this is the graph coloring and the vertex coloring in fact. In this way the edge coloring also can be possible. And edge coloring is assigning a color to each edge of G so that adjacent edges have different colors. So now edge coloring in the adjacent edges should have a different color. For that, if we consider this graph, in this graph, the same previous graph, here if we put a color in this edge, this is the black color. Now its adjacent edges means which edges are connecting through the same vertex, that edges are the adjacent edges. So if we consider this vertex, then in this vertex these 3 are the adjacent edges. So we should have 3 different colors for these 3 edges. Now in this vertex here, if we consider this edge, so then this edge and this edge, these are no more connected by any means, so that we can have these 2 edges are the same color. Now this edge and this edge, these 2 are again not connected anyway, so that these 2 edges again having the same color. Again these 2 edges having the same color because they are completely separated. Now this edge for we can't put the blue color, we can't put the red color, even we can't put the black color also. So that we should put another color. So total 1, 2, 3 and 4 colors are required to color this vertex. So this is the way by which we can color the graph by the edge coloring. One more way to color, that is the face coloring. This one is also a very important way to color a graph. A face coloring of a planar graph G assigns a color to each face or region so that no two regions that share a same boundary have the same color. So what does it mean? If this one is the graph, then in this graph according to the region we should put the color. So here look 1, 2, 3 and one outer region is the region. So these are the 4 regions given in this graph. So accordingly these 2 regions are separated. No connection between these 2 regions. Regions are connected means any one edge should be common to that. So that these 2 are the regions which should not share the same color. these two regions should have, which should not share the same color, so that we can put this region a pink color, this region also a pink color, but this one should be a different color. And the outer region definitely different from pink and yellow both, because in outer region sharing the edge for this region and this region all, so that in outer region definitely one more color is required. So total 3 colors are there. This concept is used in the color map. Now coloring the graph in this face coloring, it is quite difficult. That's why there is a way to color this type of graphs. That means face coloring, for we should take the concept of vertex coloring only. How? For that, just consider the same graph. In this graph, what we will do, at first we find out the dual of this graph. Dual by means of the regions. In each region we should consider a vertices. So we just find out the dual of this graph. After finding out the dual, so this is the dual of the given graph. So in this dual graph, now just apply the concept of vertex coloring, and the number of colors required here is the same as for the face color. So in this graph we require total, here it is the 1 color, this for the same color second color, and this is the third color. So total 3 colors are required. So in the face coloring or in the color map, we required here the total 3 colors. So for the face coloring or the color map, we should do, any graph is given, its dual at first should be find out, and in the dual graph we just apply the method of vertex coloring, that's all. Next it is the proper coloring. So proper coloring is what? A coloring of all the vertices of a graph G with colors such that no two adjacent vertices have the same color is called the proper coloring. So I hope we know what is the proper coloring now, because all of those we just do the coloring, and these all are the proper coloring if no two adjacent vertices having the same color. Now it is the chromatic number of a graph. That is the most important in the graph coloring. So what is chromatic number? The minimum number of colors required to properly color the vertex of a graph G is called the chromatic number of G. So what is chromatic number? The minimum number is required to color a graph properly. That means no two adjacent vertices having the same color. So in this way, if we color a graph, then this is called the chromatic number. The minimum number which required to color a graph properly is the chromatic number, and it is denoted by chi G. This is the notation for the chromatic number. Next, it is the chromatic index of a graph. The minimum number of colors required in an edge coloring of G is called the chromatic index of G, and it is denoted by chi dashed G. So chromatic number is for the vertex coloring and the chromatic index for the edge coloring. So there are a few important rules for coloring a graph. So what are these rules? So chi G, that is the chromatic number of G, always is less than equals to n, where n is the number of vertices in G. That is very obvious. If in a graph there are 4 vertices, then obviously the required colors are maximum 4 or less than 4. Chromatic number is 1 if the given graph G is a null graph. The null graph means only the vertices are there, no edges are there. So for each vertices, no one is the adjacent to each other, so that we can put one color to all the vertices. Now chromatic number of G is equals to exactly n, where G is a complete graph. G is a complete graph means all the vertices are adjacent to each other, so that all the vertices should put the different colors. If n number of vertices are there, so n number of colors are required, so that the chromatic number is n. Next it is the chromatic number is 2, where G is a complete bipartite graph. It is again very simple. Bipartite graph means we know it have the 2 parts. 2 parts means 2 vertex divisions. So each group of a vertex will not connected in the bipartite graph. So in each part we should put one color. So 2 parts means we require 2 colors to color the bipartite graph. So now for any graph G, the chromatic number of G is less than equals to 1 plus delta G, where delta G is the maximum degree of any vertex of G. So remember, in a graph we just observe that any vertex, that means all the vertices are given. For all the vertices we just observe which vertex have the maximum degree in the graph. So the chromatic number is one more than that maximum degree at most, otherwise less than that. If H is a subgraph of G, then chromatic number of G is always greater than or equals to the chromatic number of this subgraph. That is again very obvious. Subgraph is taken from G. So never subgraph, its chromatic number will exceed the chromatic number of the graph G. Now the chromatic number of G plus H is equals to the chromatic number of G and chromatic number of H. If two graphs are there, G and H, and if we add these two graphs, that means these two, suppose these two are the components of a graph, then the chromatic number should be the addition of all those. Next, if delta G is the minimum degree of any vertex of G with V vertices, then chromatic number of G is greater or equals to n divided by n minus delta G. Delta G is the minimum degree of any vertex. A graph is given. We observe that what is the minimum number of degree given for a vertex. According to that, we will say the chromatic number is at least n divided by n minus the minimum degree of that vertex for the given chromatic number. Now, one important theorem for the chromatic number is the Brooks theorem. This theorem states that chromatic number of G is less than equals to the maximum degree of a vertex G for a connected simple graph G unless G is a complete graph or an odd cycle. Next, it is the every C chromatic graph has at least k vertices. Every k chromatic graph has at least k vertices such that degree of V is greater than equals to k minus 1. K chromatic means k number of colors are required to color the graph. So for k chromatic graph has at least k vertices such that the degree of V should be greater than equals to k minus 1. Next, it is the if degree of V is equals to k, then at most k colors are required to color the vertices adjacent to V. That we will observe from this part also. Next, it is the two special type of graph which is required to know the graph coloring. So these two special graphs already we have discussed in our previous video lecture, but still for recapitulation I just discuss here again. The one is the cycle and another one is the wheel. What is cycle? The cycle is denoted by Cn. So a cycle Cn where n should be greater than equals to 3 consists of n vertices V1, V2, V3, Vn, and edges has to be V1, V2, V2, V3. So like this one. So here this one is a cycle, this one is a cycle, this one is a cycle, and this one is a cycle. So if the cycle is given, so for if it is the 3 number of vertices are there, so just look, if we put this one as the color green, then these two are adjacent. So this we can put the color pink both, but this one can be put pink. If we put this one also the pink, but these two are the adjacent, so that we can't put this one pink, so this one should be black. So 3 colors are required to color this graph. If this one is the graph, let us discuss this one later. At first this one, if this one is the cycle with 5 vertices, then again for this one we should put the one color. These two are adjacent, so these two having the same color. This one we can put this color because these two vertices are not connected. Now for this one we can't put the pink as well as this one, so it requires one more color, that is the black color. So 3 colors are required. Now come back to here. Here the 4 vertices are given. So here if we put this one at one color and these 2 vertices are the one more color, these 2 are not adjacent, that's why we can put the same color to these 2 vertices. Now this one we can put the same as this vertex because these 2 are not adjacent. So we required only 2 colors. And here also the 6 number of vertices are given and we required again 2 colors. So it will specifies that if it is a cycle with the odd number of vertices, then a cycle with odd number of vertices requires 3 colors, while a cycle with even number of vertices, it requires 2 colors only. Now it is the wheel. If it is the wheel, then we know in wheel means this it is obtained by an additional vertex to the cycle Cn and connect the new vertex to each of the vertices of Cn. So if this one, the outer wall is the CN, then if we put one more vertex here and we connect all these vertices with this one, then it becomes the wheel. Similarly, just look, all these graphs are here and we put one extra vertices in middle of all those wheels, all those cycles, and add the given edges, given vertices with the extra introduced vertex. So accordingly we will get these graphs. So here now the 4 number of vertices, here 5 vertex, here 6 vertex, and here the 7 vertex. So already we require 3 colors to color this graph. If we put this one and this one is adjacent to all of those, so we required one extra color to color this graph. So we require total 4 colors to color this one. For this one, only 2 colors are required, and introducing this one, it requires one extra color, so it requires 3 colors. It requires 3 colors previously. Now introducing this one needs one extra color, so the 4 colors. And this one again previously 2 colors. For this one more color is required. So in a wheel, if the number of vertices are odd, then it requires 3 colors, and if the number of vertices are even, then it requires the 4 colors. So in this video lecture, that's all. On our last video lecture, we come to know about the chromatic number of a graph. In this video lecture, we are going to discuss some theorems on chromatic number. So the first theorem is, prove that chromatic number of Kn is equals to n, where n is the complete graph. So for the proof, let Kn be a complete graph with n number of vertices v1, v2 and vn. A simple graph Kn is said to be complete if it contains exactly one edge between each pair of distinct vertices. This indicates every vertex in Kn is adjacent to every other vertex. So, if the vertex v1 is colored by the color red, then no other vertex can be colored by that color, that is red, because they are adjacent to v1. Similarly, a separate color is required to color the vertex v2 and for other vertices too. Hence, the number of colors needed to color all the vertices of Kn is n. So, we can say the chromatic number of Kn is n. If we consider one example, then let this one is a complete graph. Here, the first graph, suppose this one is colored a pink color or red color, you can see. Now, all the vertices are adjacent to this one. So, the adjacent vertices should have some different color. Now, this one is, suppose it is blue. So, for this one, again, its adjacent vertices should have all different colors. Here in the complete graph, all the vertices are adjacent to each other. Hence, the color for all the vertices should be different in the complete graph. Similarly, if a complete graph with 4 vertices is here, then we require total 4 different colors. So, a complete graph with n vertices, we required n different colors to color it completely. Now, the second theorem. The second theorem is, prove that the chromatic number of Kmn is equals to 2, where Kmn is a complete bipartite graph. So, let Kmn is a complete bipartite graph with m plus n vertices and m into n edges, where m is the number of vertices in V1 set and n is the number of vertices in V2 set. So, for example, suppose this one is the given bipartite graph. Here, V1 set contains the vertices V1, V2, V3 in this way Vm, and V2 set contains the vertices U1, U2, U3 up to Un. So now, here every vertex of V1 is adjacent to every vertex of V2. That means V1 is adjacent to all these U vertices. V2 is adjacent to all those U vertices. Then, no other vertex in V2 can be colored by the same color because they are adjacent to V1. Again, since every vertex in V1 are not adjacent to each other. That means V1, V2, V3, they are not adjacent to each other. U1, U2, U3, these all are not adjacent to each other. But any vertex of this side is adjacent to all the vertices of this side. So we can say all the vertices of V1 can be colored red. Similarly, one more color, let blue, can be used for the vertex V2. So hence number of colors needed to color all the vertices of KMN is 2. So the chromatic number of any bipartite graph is always 2. Next theorem is, it is every tree with 2 or more vertices. Every tree with 2 or more vertices is 2 chromatic. For the proof, consider any tree T. Let this one is the tree. Put the adjacent vertices with alternate colors. Continue the process until the vertices have been colored. Since there is one and only one path between any two distinct vertices of a tree T, therefore no two adjacent vertices have the same color. Just look, if we start from the first vertex and suppose this one given a particular color, then just the next label vertices should be colored a different color because these are adjacent to first one. After that, its next label vertices should be colored the first color which we assign to the first vertex, because these two vertices are never adjacent to this one. And similarly this one. After that, at the next label we should again color this previous one. In this way this process will continue. So it is observed from the above tree that vertices at odd distances from the starting vertex are painted by color, a different color, suppose it is yellow, and the vertices at even distances from starting vertex are painted by a color, different color, suppose it is red, so it is yellow, it is red. So all the odd label vertices are yellow and all the even label vertices are the red color. So this one proves the theorem, so that we can say from here that this proves that only two colors are required to color two or more vertices of a tree T. Hence T is 2 chromatic. That is, chromatic number of T is always 2. Now one more theorem. So the theorem is, a graph with at least 2 edges is 2 chromatic if and only if it has no circuit of odd length. So how to prove this one? So for the proof of this one, let G be a connected graph having circuit of even length only. Consider a spanning tree T in the G and with chromatic number 2. So if this one is a graph, here look, all the circuits which are formed of even number of edges, and the pink line depicts the spanning tree of this given graph. So as it is a tree, spanning tree is also a tree, so it requires 2 colors only. So accordingly, these are the colors to require to give the colors. Now add the edge to T one by one. After drawing the spanning tree, now the remaining edges we should add one by another in this spanning tree. Since G has no circuit of odd length, the end vertex of every edge added to T are differently colored. Thus, G is properly colored with a minimum of 2 colors. That is, G is 2 chromatic. Here look, if in this graph, this is the spanning tree. Now these two are the extra edge. So now when we add this one, so these two vertices are adjacent now and these two having the 2 different colors. Similarly, if we add this one, then these two vertices now adjacent and these two having the different 2 colors. So it will not affect the coloring of the graph. Hence, this is the total number of required color to color a graph if the given graph having all even number of circuits. So total 2 colors are required. So conversely, if G has a circuit of odd length, then we need at least 3 colors for properly coloring of that circuit. That implies the chromatic number of G is greater or equals to 3. Hence, G cannot contain a circuit of odd length. So, if this one we consider, then this one is a circuit of odd length, and with odd length, it always requires minimum 3 colors. So, from here, we can have an observation that for a non-null graph G, the following statements are equivalent. First statement is G is 2 chromatic, then G is bipartite and G has no circuit of odd length. So these are the few theorems on the chromatic number. In this video lecture, we are going to discuss about the problems on chromatic number. But before discussing the problems, some special rules and theorems we should recapitulate once more. So the first theorem or first rule is chromatic number of G is always less than equals to 1 plus delta G, where delta G is the maximum degree of any vertex of the graph G. The second rule is chromatic number of G is greater than equals to n divided by n minus of delta G, that is the small delta G, where small delta G is the minimum degree of any vertex of G where n is the number of vertices. So this is the maximum degree count for the vertices in the given graph and this is the minimum degree for the vertices in the graph. So according to the maximum and minimum, we can find out the chromatic number, the threshold of chromatic number accordingly. Next, it is the chromatic number of G is equals to K, where G should have K vertices with degree at least K minus 1. That is, degree of V is greater equals to K minus 1 for K chromatic graph. That means, if in a graph, we will find out that the degree of the vertices are K greater than equals to K minus 1, at least that is for the K number of vertices, then we can say the graph is K chromatic. Now, one more theorem is, that is the Brooks theorem. It states that chromatic number of G is less than equals to the delta G, where delta we know that is the maximum degree of any vertex in the given graph for a connected simple graph G, unless G is a complete graph or an odd cycle. Next, it is the Koenig's theorem. So Koenig's theorem states that a graph G with at least one edge is 2 chromatic if and only if it has no circuit of odd length. So these are the theorems which we should know previously before the solving of the problems on chromatic number. So the first problem is find the chromatic number of the following graph. So this graph is given and we are supposed to find out the chromatic number for this one. So how to find out this one? So initially 3 colors are required for the vertex V1, V2, V3 of the triangle. We know if a triangle is there, then to color this one we require minimum 3 colors. So if we consider V1, V2 and V3 this triangle, then to color this one we require 3 colors. So these are the 3 colors we put. Now we assign 3 distinct colors, these 3 here. So now since the vertex V4, so this vertex V4 is adjacent to V1 and V3, then definitely so V4 not get the color of V1 and V3, but one more color which we provided to V2, that should be colored to V4, so that we should give the V4 as the same color as V2. Now one more vertex is left. This vertex is adjacent to V1, V3 and V4, all these 3. So it is very obvious that among these 3 no color can be put to the vertex V5. So we required one more color to color the vertex V5. So that one extra, the 4th color is required. So accordingly we can say that the chromatic number of this given graph is 4. This is the straightforward trial and error method. Now in the next problem we apply the theorems. So now in the second problem is find again the same type of problem, find the chromatic number of the following graph. So this one is the given graph and we are supposed to find out the chromatic number for this one. So at first we observe the graph very carefully. In this graph we should find out that each vertex having degree 3. All the vertices are of degree 3. So here from the theorem that chromatic number is always less than equals to 1 plus the maximum degree of G. So that will implies that the maximum degree here for the vertices is 3. Any vertex you may consider, its degree is 3 and that is the maximum degree. That's why delta G is equals to 3. So chromatic number is either 4 or less than that. Again, the minimum degree if we consider, then it is also 3 here. So that from the property that chromatic number of G is greater than equals to n divided by n minus delta G, it will implies that it is total number of vertices are 4. So that it is 4 divided by 4 minus 3 is equals to 4. So we will find out that the chromatic number is greater than 4 and it is less than 4. So hence both if we sum up, then it will implies that the chromatic number of the graph is 4. So using these theorems, we just verify that the chromatic number is 4. Now the next problem. In this problem, the question is find the chromatic number of the following graph. So this one is the given graph and we are going to find out the chromatic number. So initially, again we should observe the graph very carefully and we will find out that the maximum degree at first we find out. So if we observe the degrees of each vertices, then its degree is 3, 3, 3, then it is 4, then it is also 4, 3 and this its degree is 1, 2, 3, 4. So this is the highest degree. So 4 is the highest degree in this graph. So according to the property that chromatic number of G is less than equals to 1 plus delta G, we will find out 1 plus 4 is equals to 5. That means chromatic number for this graph is at most 5 or less than 5. Now since G contains odd cycle means if we consider the triangle V2, V3, V4, then this one creating an odd cycle. That means the graph contains odd cycle. So if any graph contains the odd cycle, then odd cycle for we required minimum 3 colors, so that the chromatic number is definitely greater than 3, greater than or equals to 3. That means chromatic number lies in between 3 to 5. So it may be either 3 or 4 or 5. So now we should inspect that the chromatic number is 3 or 4 or 5. Suppose the chromatic number of the graph G is 5. Then G should have 5 vertices with degree at least 4 or more. That we have a property. But there are exactly 3 vertices V4, V5 and V6 of degree 4. Just check. V4 having the degree 6, having the degree 4, V5 having the degree 4 and V6 having the degree 4. So there are 3 vertices only with degree 4. That's why we will see that the chromatic number of G definitely not equals to 5. Now 3 colors are required for the vertex V2, V3, V4 of the triangle. If we consider this triangle, then 3 colors are required to color these 3 vertices. Now, if we consider the vertex V5 now, then this one is adjacent to V3 and V4, so that its color should be different from these 2. So it can be having the color same as V2. So that this is the color. Now V6 vertex, if we consider, it is adjacent to V5 and V4, and likewise it should have the different color from V5 and V4 and let it be the same color as V3. Next it is V7. If we consider this vertex, then V7 is adjacent to V5 and V6, so that definitely it should put a different color from these 2 and it should be taken the color of V4. So V4, V7 have the same color. So now one extra vertex, one more vertex is left, that is V1. So V1 is adjacent to V7, V2 and V6, all these 3. So as this is adjacent to all these 3, so it have definitely a different color from V7, V6 and V2. So all these 3 colors are used here, so it should require one extra color, that is the 4th color. So that we can say that the chromatic number of the given graph is 4. So here is the explanation is written also. So the chromatic number for this given graph is 4. So in this way we can find out the chromatic number of the given graph. So one more example is there. So that one is the find the chromatic number of the following graph G. So now the graph is given this one. Here the graph has no circuit of odd length. Just check it. If we consider the circuits like this one, if this one is a circuit, it having 4 edges. Now, if we consider this one having a circuit, so this one is also the graph, that also a circuit with the 4 edges. So here all the even circuits exist. That means no circuit of odd length is here. Hence, by Koenig's theorem, we know that the graph G is 2 chromatic. From the Koenig's theorem, we know that if a graph having no odd circuit, then its chromatic number is 2. Hence, the proof and the chromatic number of this graph is 2, which is our requirement. Next problem is find the chromatic number of the following graph. So this one is a graph given and we are supposed to find out its chromatic number. So this graph is very obvious that no circuits are there and it is a tree. We know a tree, if it is, then it is a kind of bipartite graph and its chromatic number is always 2. So the chromatic number for this type of graph is 2. One more example is given. Find the chromatic number of the following graph. So this one is a given graph and its chromatic number we are supposed to find out. So in this graph, we can observe that this is definitely not a bipartite graph. As it is not a bipartite graph, so its chromatic number is neither 2 nor 1. So that we can say this is a non-null graph. Definitely, if a graph is a null graph, then only its chromatic number is 1. If it is a bipartite graph, then its chromatic number is 2. Otherwise, it is more than that. Now, the graph is connected and this given graph is connected and its highest degree count we should find out. So, for this vertices, the degree 3, 3, 3, 3 and 3. Here it is also 3, 3, 3, 3 and 3. So, all the vertices having degree 3. So, the maximum degree count is 3. So, for all the vertices and it is not a complete graph. Just look at the graph carefully. All the vertices having the same degree 3, but still it is not a complete graph. So, it will satisfy all the conditions of the Brooks theorem. In Brooks theorem, we know that the chromatic number of G is less than equals to the highest degree of a vertex for a connected simple graph G unless G is a complete graph or an odd cycle. So, it is the Brooks theorem satisfying, it satisfies all the conditions for the Brooks theorem. So, we can say that the chromatic number of G is less equals to the highest value of the degree of the highest degree of the given graph is equals to 3. So, hence the chromatic number should be here 3 because it is not 1, not 2 and it is not more than 3. So, that it is definitely 3. So, the chromatic number for this graph is 3. So, in this way, we can find out the chromatic number of different graphs. So, remember, not required for all the graphs to inspect that how many colors are required. But some properties, some theorems also we can apply to find out all those chromatic numbers. That means, if we apply all those theorems, then we can have a minimizing form or minimizing solutions for all those to get the chromatic number. In this way, we can find out the chromatic number. So, I hope you understand what is chromatic number, what are different theorems and properties and how to solve all those problems for the chromatic number. In this video lecture, we come to know about clique. Clique is again a type of subgraph. So, a clique of a graph G is a complete subgraph of G. So, what is clique? A clique of a graph G is a complete subgraph of G. What does it mean? It is denoted by first of all omega G. And in other words, we can say a set C is a clique of the graph G if and only if C is the subset of the vertex set of G and U and V are the two vertices of C where U not equals to V implies UV, that is the edge UV belongs to the edge of the graph G. So what is click, that we explain with an example. So for example, let this one is the given graph. In this given graph, we should find out that what is the complete subgraph included in this graph. So complete subgraph means a graph if having two vertices, then it have exactly one edge. If three vertices are there, then there are exactly three edges. That is the triangle. If there are four vertices, then it is like this one. So if this one is the given graph, then here we can find out the complete subgraph, which is maybe this one. So this one we can say it is a click, and this click contains the contains the vertices A, F, C and B. So this one is a click for the given graph, and look, this one is a complete graph. So being a click, it has to be a complete graph definitely. Now if we consider this one as the subgraph, then it is not complete, so it is not a click. If we consider only these two vertices, that means ED, so if we consider this one as a subgraph, then it is a click because it is a complete subgraph. Now another example we may consider. So if this one is an example, here we will find out that if we consider this triangle, that means this one, then it is a complete subgraph, then it is a click, and it contains the edges E, G and F. Likewise, this one is another click because it is also the complete subgraph from here. So this one we can say it is the click for the given graph, and it is denoted by A, B, C, D. These are the vertices included in this click. Not only these two, but if we consider this one only, that means D and E, means this one, then it is again a click. So here we should remember that subgraph induced by a click is a complete graph. We know what is the induced subgraph. So the subgraph induced by a click is a complete graph. For any given graph, whatever be the clicks are there, these are the complete graph. In fact, we can say that any click which contains these vertices, among these vertices there are all vertices are adjacent to each other. Hence, it is a complete graph. So we can say subgraph induced by a click is a complete graph. Now, from here we have two type of click. One is the maximum click, another one is the maximal click. So what is the maximum and the maximal click, and what is the differences between these two? First of all, it is the maximal click. So a click is maximal if and only if it is not a proper subgraph of another click. So now look, here in this one is a graph where these are the three clicks, and that is because if we consider GF as a click, then what happens? We can say if we consider the subgraph only containing the vertex F and G, then definitely it is a subgraph, but it is not the maximal click. It is a click, but it is not a maximal click, because if we consider E, F, G as the subgraph, that means this one, then its subset becomes the vertices FG. If we consider only that portion, that means FG, then what happens? We can say this one is a click, but this is not a maximal click because be a proper subgraph of any other click. So this one individually is a maximal click, this one individually is a maximal click, this one individually as a maximal click, because no one is the proper subgraph of any other given subgraph which is a click. Now it is the maximum click. What is the maximum click? A maximum click of a graph G is a click with as many or more vertices than any other click in G. So what does it mean? That here among all the maximal clicks, which maximal click have the highest number of vertices, that one is called the maximal click. So for this particular graph, 3 clicks are possible, and among these 3, these all are the maximal click, but among all these 3, this one is the maximum click. So maximum click is with the highest number of vertices, and this highest number is called the click number. So the first of all, we should find out the maximum click. After finding out the maximum click, we find out that how many number of vertices are there in this maximum click. That particular number is called the click number. So, for this given graph, the click number, which is denoted by WG, is 4. For this one, the click number is again 4 because this is the highest click or the largest click or the maximum click. Definitely it is maximal also. So here the click number is again 4. So this is our click. But now we should do some example for the click. So here find all clicks in the following graph and find the click number also. So these are as your homework and you can do by yourself. So this one is a given graph. Your requirement is to find out the clicks, all possible clicks, and among them which are the maximum click. So maximal click and the maximum click, both you should find out for this given graph and hence find out the click number. So this is your first example. Now this is your second graph. For this one also you are supposed to find it out. And one more graph, that is this one. So for this one also you should find out that what is the maximal clicks and the maximum clicks and the click numbers too. So try by yourself these all. If you will get the answer, then post your answer in the comment box. In this video lecture, we come to know about independent set or vertex independent set. This one is again the part of subgraph. So now a subset of a vertex set of a graph G is independent set if and only if it contains no pair of adjacent vertices. So what does it mean? So for example, this one is a given graph and here the independent set means we should find out those set of vertices where the vertices which have no connections, that means they are not adjacent to each other. So if we consider from this graph the set BD, so B is this one and D is this one, so they are not connected, so these two are not adjacent. That's why we can say this is the independent set. Now it is the AC. AC means A is this one and C is this one. Again they are not connected, so these two are independent. Now it is ED. E and D. These two are again no connection is there, so these are independent. AD. So A is this one and D is this one, so no connection between them, so this is independent. Again AE. These two again we can say these are independent sets. And one more, it is AED. So these three are there. Among AED, no connectivities are there. No one is adjacent to each other. So all these we can see as the independent set. Now here we categorize something according to the properties. So first of all, so BD, AC and AED. That means BD, AC and AED. These three independent sets are called the maximal independent set. That is because these three have no proper subsets which are independent of these sets for this graph. So these are called the maximal independent set because no proper subset. These are not the set of any proper subset which are independent again. Now the set this one AED. AED is the maximum independent set because it is the highest number of vertices containing. That's why this is called the maximum independent set. Now the maximum independent set, according to that we will find out the vertex independent number which is denoted by alpha G. If we consider this graph, then for this particular graph the vertex independent number is 3 because in the maximum independent set the number of vertices are 3. Now here the pink sets, that means it is ED, AD and AE. These are independent sets but not maximal because these are the proper subset of AED. We know that AED, this one is the independent set. And look, ED is the subset of this one, AD is the proper subset of this one and AE is also the proper subset of this one. as these three are the proper subset of the set AED, that's why we will say that these are independent set but not maximal independent set. So now how to find out the independent set, that is the maximum independent set. How to find out the maximum independent set? So for that there are two steps. First of all, we just find out the complement of the given graph, and after that we find out the maximum click for this complemented graph. So what we will do, initially this one is our given graph. If we find out its complemented graph, then it should be this one. So this one is the complement of the given graph. You just draw by yourself. Look, this one, this dotted line denotes your original graph, and this one, these lines are joining to get the complementation of the given graph. So after getting the complement of this graph, what we will find out, that what is the maximum click for this graph. So for maximal click, we will find out that BD creates a click because this is the complete subgraph of the given graph, given this complemented graph. Now AC, this is another click, and ADE, this one is another click. So among these three, definitely ADE is the maximum click for this given complemented graph. Now, so this click is the maximum independent set of G. So at first we should find out the complement of the given graph, then find the maximum click for this complemented graph, and this maximum click contain which vertices. These are the independent set for the given graph. That means for the given graph G, our maximum independent set is AED, and according to this one, the maximum click containing the vertices ADE, both are same. Hence, by this way, we can find out the maximum independent set for the given graph. Now, here are the clicks which we will say about this one. So if this is the given graph, just look at here. This one is the independent, this one is the complemented graph, and its three clicks are this one, and this one. So that the maximal click is here ADE. So which is the maximum independent set of G. So for example, here find all the independent sets of the following graph. Hence, find the vertex independent number of G. If this one is your given graph, so for this graph, you are supposed to find out the independent sets, all independent sets, and find out the vertex independent number also. Now it is about the perfect graph. So what is perfect graph? That is again the continuation of the spanning subgraph, induced subgraph, click and all. So to get what is perfect graph, for that we just make this previous all videos for the subgraph and the spanning subgraph and the induced subgraph and the click and all. So what is perfect graph? A graph G is said to be a perfect graph if its chromatic number and click number both are same. We know what is chromatic number. Chromatic number is the number of maximum colors required to put the perfect coloring of a graph. Now, what is click number? That again we come to know. Click number is the number which is we will find out by deletion of one or two or more vertices, and which one is the complete subgraph from the given graph. So that according to that, if we will find out for a given graph, if the chromatic number and the click number both are same, then we can say the graph is a perfect graph. Otherwise, it is an imperfect graph. So for example, if this one is the given graph, here just look how many colors are required. So at first, if we put these two vertices as two different colors, then this one has to be a different color because this one is the complete graph and it is an odd cycle which requires 3 colors definitely. Now we can put this one as this one. The both are the same color and these two should be the same color. So total 3 different colors we required. So the chromatic number is here 3. Now the click number for here the maximum click we can find out which should contain the 3 number of vertices. So that the click number is 3 here. and we will find out that the chromatic number and the click number both are same. So that means chromatic number is equals to the click number. So that will implies G is a perfect graph. Now here is the another example. If we consider this graph, so here the number of colors required are 1, 2, 3. Then here 3. Total 3 number of colors are required. So its chromatic number is 3. And again definitely this one is a click, this one is a click, and this one is another click. So the maximum click contains the 3 vertices. So the click number is 3 here. And both are same. Hence it is also a perfect graph. If we consider one more example, then for this one, we will find out that the chromatic number is 4. Just have a look. Here the chromatic number is 4 and the click number for the maximum click, that means the complete maximum complete graph, maximum complete subgraph which contains in this graph is this 4. That means this one is the complete subgraph for the given graph and it will contain 4 vertices. So total number of vertices are 4 in the click here. So maximum click, so that both are same. So G is a perfect graph. Now one more example is here. So this one is a cycle with odd number of vertices. A cycle with odd number of vertices, we know it requires 3 colors always. So this one is the chromatic number for this graph. Now for the click number, here the maximum subgraph, which is a complete subgraph for the given graph, we can consider any 2 vertex joining an edge, any two consecutive vertex definitely. So that here the maximum click contains 2 vertices anywhere. So that it is click number is 2. Here the chromatic number is 3 and the click number is 2. So G is not a perfect graph. So this is the all about perfect graph. In this video lecture, we are going to cover up the chromatic polynomial. So what is chromatic polynomial? At first we should understand that. After that we should find out that how to find out this chromatic polynomial. So before starting that, just let me tell you, chromatic polynomial is a function of a graph. Chromatic polynomial is the representation of a graph in the functional way. By the function, we can find out how many total colors are required to color the graph properly. That means a polynomial form we will provide for a graph. On that polynomial form, depending upon the input values or depending upon the criterion or characteristics of the polynomial, we can say that how many different colors are required. That means what should be the chromatic number of the given graph that we can verify. So what is chromatic polynomial? A graph G with n vertices can be properly colored by lambda or fewer colors. If a graph G with n vertices is given, then it can be properly colored by the lambda or fewer colors. Lambda is the number of colors. So the different lambda colorings of a graph can be expressed by the means of a polynomial. This polynomial is called the chromatic polynomial in lambda of G and it is denoted by P and lambda. P for the polynomial, N for the number of vertices and lambda is the number of colors used. So this function P and lambda yields the number of way of properly coloring of G using lambda or fewer colors. So initially, if n number of vertices are given, then we can have at most n number of colors. Definitely the color not exceeds the n, but we can initially choose that total n number of colors. So that chosen colors or that initially considered color is lambda. Now your chromatic number should be either lambda or less than lambda. So how to find it out, the chromatic polynomial? So let I be the different ways of properly coloring G using exactly I colors out of lambda colors. If their total lambda colors we have considered and out of lambda, if I number of colors are required to color G properly, then how many different ways are there to color the graph G, that number is denoted by Ci. So that we can use the binomial to find out the Ci. So here I colors can be chosen out of lambda colors in how many ways, that we should at first find out. So it is lambda Ci. So that is the, from binomial we will find out this one. So this is the different number of ways by which we can choose I number of colors from the lambda colors. So there are Ci into lambda Ci different ways of properly coloring G using exactly I colors out of lambda colors. So now, since I can be any positive integer from 1 to n, as it is not possible to use more than n colors on n vertices, the chromatic polynomial is a sum of these terms. So that is, we will find out that the chromatic polynomial is Pn lambda is equals to summation of I is equals to 1 to n, then Ci into lambda of Ci. What does it mean? That if required color is 1, 2, 3, 4, 5 in this way up to n, then what should be the total number of ways to find out the different coloring. So this one we can write in this format. So it is, if we expand this one, then we will find out C1 lambda by 1 factorial plus C2 lambda into lambda minus 1 by 2 factorial, and all. These all are the binomial expansions, nothing else. So now after that, each Ci has to be evaluated individually for the given graph. For example, any graph with one edge requires at least 2 colors for proper coloring. Therefore, C1 should be 0. If 2 vertices are given and one edge given, then it is obvious that these 2 vertices are adjacent to each other. So it requires minimum 2 colors. So with one color, if we want to color, then there is no option to color in this manner. That's why it is C1 is 0. Again, a graph with n vertices and using n different colors can be properly colored in n factorial ways. So if suppose 3 vertices are only given, so that these are the connected vertices. So these are adjacent to each other. So if we put this one a color 1 suppose, then there are total 3 colors. Among them, if I put this one is the first color 1, so then it is obvious that this one should be chosen remaining 2 colors from, and this one should be chosen from the remaining 1 color from. So that the total number of total different ways I can put this vertex the color as 3, any 3 color of these 3. After choosing the 1 color for this vertex, the remaining vertices are 2 different colors are there. So for this vertex we have the 2 options to choose, and for this vertex we have 1 more option to choose. So if we multiply this way, then we can find out that how many different ways we can color the graph. So it is the 3 factorial we can see. Similarly, if there are total n number of vertices and n colors are provided, then by using the n different colors, it can be possible to color in n factorial ways. So if the maximum number of colors are taken, maximum color means the number of vertices and the number of colors are same, that is the maximum number of color which we can consider. So for the maximum number of colors, it should be n factorial always. So how to find out this chromatic polynomial, that we will explain with an example. So find the chromatic polynomial and the chromatic number for the given graph G. So if this one is the graph, then how to find out the chromatic polynomial? So in this graph, there are total 5 vertices are given. So n is equals to 5. So what to do here? The P5 lambda we should find out. So P5 lambda should be, it is C1 lambda, the first term. The second term is C2 lambda minus 1 by 2 factorial, then plus C3 lambda into lambda minus 1 lambda minus 2 by 3 factorial. This is the next term. After that it is C4 into lambda minus 1 into lambda minus 2 into lambda minus 3 by 4 factorial plus C5 into lambda minus 1 into lambda minus 2 into lambda minus 3 into lambda minus 4 divided by 5 factorial. Since the graph has a triangle V1, V2, V5, just now emphasize on the graph. So V1, V2 and V5, V1, V2 and V5. This one we can consider the three vertices which are connected. So this is forming a triangle. So it will require at least three different colors for proper coloring. So if triangle is formed, that means it requires definitely three colors to color it properly. So that C1 and C2 should be 0 because one color and two colors are not possible to consider. So minimum three colors are required here. So accordingly C1 should be 0 and C2 should be 0. And C5 always we know as total number of vertices are 5. So C5 is definitely 5 factorial always. Now with three colors V1, V2, V5, the three colors of the vertex V1, V2, V5 can be colored properly in 3 factorial ways. V1, V2, V5 having three colors. So these three colors can be chosen in 3 factorial ways. So having done that, we have no more choices left because vertex V3 must have the same color as V5 and V4 must have the same color as V2. Just look at the graph again. We have colored V1, V2, V5. Now for V3, V3 is adjacent to V1 and V2. So V1, V2 as these are adjacent to V3. So V3 should have a color which is same as V5. Now V4, this one is adjacent to V5, V3 and V1 so that its color should be the same as V2. So in this way, we require only the three colors to color this graph properly. So with three colors, there are the 6 ways to color the graph properly. So now it is similarly with the 4 different colors. That means if we have the 3 colors only, then using these 3 colors, we can color it in the 6 different ways. If the 4 different colors we have considered for coloring this graph, then what happens? So the first vertex of V1 can be taken any 4 colors. So next vertex can be taken any 3 colors of that. So in this way, so 4P3, that is 24 different ways are there to color the vertex V1, V2, V3. V1, V2, V3 having 3 different colors and total 4 colors are provided. So out of 4, if we choose any 3, so that how many different arrangement can be possible? It is 4P3. So this is 24 ways are there to color the vertex V1, V2 and V5. Now the 4th color can be assigned to the vertex V3 or V4. So now let us choose the remaining vertices, that is V3 and V4. So after considering 3 colors for these 3 vertices, we have left one more color. So that color can be assigned to V4 or V3, anyone. Thus there are 2 choices for either V3 or V4. So after using these 3 colors here, one color left, and if we choose the vertex V4, then it can have color on the same color as V2 because V2, V4 are not adjacent and one color is left. So total 2 colors are left there to color the vertex V4 and the same for V3 also. So the 5th vertex provides no additional choice. So among these 2 colors, if we put one color V4 in V4, then for V3 we have only one choice left. So accordingly, we can say that the C4 should be 24 for coloring these 3. Then 2 is the number of colors to coloring V4 and one color left to color the remaining vertex. So total number is 48. So substituting this coefficient of C1, C2, C3, C4 and C5 in the polynomial, we will find out the polynomial as C1, C2, 0. So first 2 terms are 0. Now for C3 it is 6, we will find out. So 6 into lambda minus 1 into lambda minus 2 by factorial 3. Then plus of 48, that is C4 is 48. So 48 into lambda minus 1 into lambda minus 2 into lambda minus 3 by factorial 4 plus 120. 120 is for the C5, that is the 5 factorial into lambda minus 1 into lambda minus 2 into lambda minus 3 into lambda minus 4 by factorial 5. Now if we simplify this one, then after simplification, we will find out this one as the polynomial. Here is the simplification and the polynomial is lambda to the power 5 minus 8 lambda to the power 4 plus 24 lambda cube minus 31 lambda square plus 14 lambda. This one is the chromatic polynomial of G. Now, just observe this graph. Here, never ever you will find out any constant term in this polynomial. Because constant term means if you put lambda is equals to 0, then even you will get it is a non-zero value. Now for the chromatic number, we should substitute the lambda values as 1, 2, 3 in this way. And for which minimum value of lambda, we will find out the polynomial value is not equals to 0. That lambda value is the chromatic number of G. So if we substitute here lambda is equals to 1, then what happens? If we substitute 1, then it is 1 minus 8 plus 24 minus 31 plus 14. If we sum up, then we will find out this value is 0. So definitely lambda is equals to 1 should not be the chromatic number for this polynomial. If we put lambda is equals to 2, you should provide the lambda is equals to 2. So if we put the lambda is equals to 2, then we will find out this value is again 0. You can try by yourself. If we put lambda is equals to 3, then it is a non-zero value. So that we can say the chromatic number of this polynomial is 3. So now to find the chromatic number from chromatic polynomial, substitute for lambda as 1, 2, 3, we will find out this chromatic number. So for which minimum value of lambda, p and lambda becomes non-zero, that is p and lambda is not equals to 0, that particular lambda value is the chromatic number of G. Here for lambda is equals to 3, we will find out this is non-zero, hence the chromatic number is 3 here. Now here I am providing you the chromatic polynomial for few certain graphs which are the known graph. For them I am providing you the chromatic polynomial. So if it is the null graph with n number of vertices, then its chromatic polynomial is lambda to the power of n. If a complete graph with n vertex is there, then its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2. In this way it is up to lambda minus n plus 1. If it is a tree, then its chromatic polynomial is lambda into lambda minus 1 to the power n minus 1. If it is a cycle with n number of vertices, then it is lambda minus 1 to the power n plus minus 1 to the power n into lambda minus 1. If it is a wheel, then its chromatic polynomial is lambda into, in whole bracket it is lambda minus 2 to the power n minus 1 minus of minus 1 to the power n lambda minus 2. And if it is a path graph means it is a path means nothing but the bipartite graph. So then its polynomial is lambda into lambda minus 1 to the power n minus 1. Tree and path graph for both the same polynomial definitely be there because both are the bipartite graph. Now some important observations of chromatic polynomial. Okay, just let me tell you that all these chromatic polynomials, how to find it out, that I will discuss in my next video lecture. Now it is some important observations of the chromatic polynomial. So the first observation is the constant term of any chromatic polynomial is 0. The second observation is the sum of the coefficients of the chromatic polynomial of any graph is always 0. It is if it contains at least one edge. So if a non-null graph for whatever be the chromatic polynomial, you will find out if we add all the coefficients in the chromatic polynomial, then the total sum is always 0. For example, in the last example, we have get this one as the chromatic polynomial. Here the coefficient for the first term is 1, for this term it is minus 8, for this term it is 24, this is minus 31 and this is 14. And if we add all those, then we will find out this is as 0, and it always be happen for any chromatic polynomial. If you will not find so, then you can a wrong one. The coefficient of chromatic polynomial have alternate in sign. Just observe here, the first one is positive, then negative, positive, negative, positive. So always it will happen that the coefficient of chromatic polynomial is an alternate in sign. the absolute value of the second coefficient, that is the coefficient of lambda to the power n minus 1 in the chromatic polynomial of a graph, equals the number of edges in the graph, and that is the given. If we consider this example here, we will find out that the second coefficient having the numerical value 8. So we can be sure that the given graph have total 8 number of edges. Just have a look. If this one is the graph, here count the number of edges. It is 1, 2, 3, 4, 5, 6, 7 and 8. So total 8 number of edges are there. And always this coefficient denotes the number of edges in the chromatic polynomial. Next observation is the highest power of lambda in the chromatic polynomial of a graph is the number of vertices n in G. So highest power of lambda is here, it is 5. So that highest power always denotes the number of vertices in the given graph. So if you have a chromatic polynomial, so observing the chromatic polynomial, you can understand that how many vertices are there, how many edges are there, what should be the total number of colors required to color this polynomial and all. So these all things we can find out from the chromatic polynomial. So that's all for today. In the next video lecture, we discuss the theorems, some theorems on chromatic polynomial, and afterward we discuss few examples for the chromatic polynomial. In this video lecture, we discuss some theorems on chromatic polynomial. So the first theorem is prove that chromatic polynomial is a polynomial in lambda. So chromatic polynomial, we are saying it always a polynomial. So it is really a polynomial or not, that we discuss in this theorem. So how to prove it? Let Pn lambda yields the number of ways of properly coloring of G with n vertices using lambda or fewer colors. So initially a graph G is given with n number of vertices, and we should choose lambda different colors to color the graph G. Definitely lambda value should be less than or equals to n, the number of vertices. Now out of this lambda, if we choose any color means any I number of colors to color the graph, suppose properly. That means if we choose I different colors from the lambda colors to color the graph properly, then there are definitely Ci different ways are there. From the lambda, if we select I different colors, and if it is possible to color the graph properly by using I different colors, then by using I different colors out of lambda, there are let Ci be the different ways of properly color that graph G. Again, these I colors can be selected from lambda different colors. Total lambda number of colors are there. From there we have chosen the I different colors. I may be 1, 2, 3, 4, anything up to lambda. It definitely not be 0, because a graph coloring means at least one color we should require. So now if I colors can be selected from lambda different colors from the selected colors lambda, then there are definitely lambda Ci ways. Out of lambda, if I colors be taken, then there is possibility of different number of ways of choosing I such colors are lambda Ci. And using this I colors, if we color the graph properly, then this different coloring can be possible by Ci different number of ways. So the total number of coloring, that means the way of coloring of a graph using I colors is Ci into lambda Ci ways. So hence the total number of colors, the total number of ways of properly coloring of G using exactly I colors from lambda or fewer color is this one. When I is equals to 1, then it should be Ci lambda C1. When I is equals to 2, then it is C2 lambda C2. In this way, we will find out the different number of ways to color by choosing 1, 2, 3, 4. In this way, up to lambda number of colors. And finally, if we add all of them, then we will find out the total number of ways by which we can color the given graph using the lambda different colors, so that we can find out this one, where this lambda ci we know from the binomial. This one is lambda into lambda minus 1 into lambda minus 2. In this way it is up to lambda minus I plus 1 divided by factorial of I. So if we sum up this one and finally we expand this one, then definitely we will find out it is a polynomial in lambda. Hence the proof. Next theorem is prove that the chromatic polynomial of a complete graph with n vertices is Pn lambda is equals to lambda into lambda minus 1 into lambda minus 2. In this way it is up to lambda minus n plus 1, where n is the number of vertices. So what is the second theorem? The proof that the chromatic polynomial of a complete graph with n vertices is this one. So now how to prove this one? Initially the given graph is a complete graph. So let Kn be the graph, which is a complete graph with n number of vertices. So since Kn is complete, therefore it contains exactly one edge between each pair of distinct vertices. So with lambda colors, there are lambda different ways of coloring any selected vertex of a graph. So a second vertex can be colored. So a second vertex can be colored properly in exactly lambda minus 1 ways. Total n number of vertices are there, lambda number of colors we have chosen. So the first vertex can be colored in the lambda different ways, because out of lambda we can choose any color in lambda ways. After choosing the one particular color from lambda, then the second vertex can be chosen in lambda minus 1 different ways. Then the third vertex similarly can be chosen in lambda minus 2 ways, and the fourth vertex is lambda minus 3 ways, and so on. So all the vertices we can choose in this way. Then for each vertex we will sum up that for first vertex it is lambda, for second it is lambda minus 1, for third it is lambda minus 2. In this way it is up to nth vertex, it should be lambda into lambda minus of n plus of. Finally, the nth vertex can be properly colored in lambda minus n plus 1 ways. So by principle of counting, the graph Kn can be colored in lambda into lambda minus 1 into lambda minus 2. In this way up to lambda minus n plus 1 ways. Thus, this one is the chromatic polynomial for a graph which is a complete graph with n number of vertices. Hence the proof. Next, the third theorem, and the third theorem is prove that the chromatic polynomial of null graph G with n vertices is lambda to the power of n. So a null graph means there are any number of vertex you might have, but no edges should be there. So that if n number of vertices are there, so we consider a graph G with n vertices. So since no vertex in null graph G is adjacent to any other vertex, therefore each of them can be colored independently by using lambda different colors in lambda to the power n ways, as each vertex can be colored by lambda ways and there are n such vertices. If it is a null graph, so null graph means only the vertices are there. So any vertex if we color, so total lambda number of colors are there, then we can choose any one color from out of this lambda. So there are total lambda ways to choose the first color. Again, for this one, as these are not adjacent vertices, that's why again we can choose lambda different colors for coloring this vertex again. For this one, again these are not adjacent to any other, so that lambda number of colors again we can consider for this one again. Similarly, whatever the vertices are given in a null graph, for each and every vertex we can choose lambda different ways or lambda different colors from the lambda different colors, so that we can say for each vertex the total number of ways by which we can choose a color is lambda. Hence, depending upon the total number of vertices, the polynomial should be then lambda to the power n. That is by the principle of counting we will find out. Hence the proof. Now one more theorem in this video. So that theorem is, here it is the fourth theorem. So prove that the chromatic polynomial of a tree with n vertices is lambda into lambda minus 1 to the power n minus 1. This theorem, if we want to prove, then we use the mathematical induction method. So what we will do, at first we will consider that let T be a tree with n number of vertices. So initially given graph is a tree, so let us consider a graph is T, which is a tree with n number of vertices. So this one we are going to prove by the mathematical induction. So initially let n is equals to 1. The number of vertices are given in the tree is 1. Then it can be colored by lambda different ways using the lambda colors. So that from the theorem we can write it is lambda into lambda minus 1 to the power 1 minus 1. As we consider n is equals to 1 by the mathematical induction, we just substitute the value n for 1. So that we will find out this value is lambda, which is the lambda different colors to color the one vertex which we have in the tree. So that this one proves that for n is equals to 1, the theorem is true. Hence, the given statement is true for n is equals to 1, we can see. Now suppose that this theorem is true for m. That means when n is equals to m, then the theorem is true. Hence, we can assume or we can have that Pm lambda is equals to lambda into lambda minus 1 to the power m minus 1 by the mathematical induction. Now we have to prove that the tree or that the theorem is true for n is equals to m plus 1. So the number of vertices now it is m plus 1. So what we will do initially with the tree where the tree having the m plus 1 number of vertices, we should delete one vertex, one pendant vertex from this tree. That means from this tree where the total number of vertices are m plus 1. So after that deletion, what happens? The tree will contain total m number of vertices. We have started from the m plus 1 number of vertices. Now if we delete one vertex, then what will happen? The tree will have total m number of vertices. We will delete one pendant vertex there. So if we give an example here or just a pictorial notation, then this one is a tree, suppose it having the m plus 1 total vertices, and these are the two vertices we consider, one is u and one is v. Now we delete this vertex v. So then what happens? The remaining tree having the total m number of vertices, and after removal of this one, this edge also be removed. So that what we will find out, after deletion of one pendant vertex v from T, it contains m vertices, and this tree T minus v, the chromatic polynomial should be this one, lambda of lambda minus 1 to the power m minus 1. So this is by induction hypothesis. Since v is the pendant vertex of T, it is adjacent to only one vertex, say u. That means as v is the pendant vertex, then it is obvious that it is the adjacent to exactly one vertex. So therefore, v can be assigned with any of lambda minus 1 colors. Tree means no cycles are there. So whatever be the colors lambda are there, if we have, then to color this v, definitely except this color, we can choose any other colors for the previous one. So total lambda minus 1 different colors are required. So by principle of counting, the chromatic polynomial of T will be what then? For v, we should include lambda minus 1 with the polynomial lambda of lambda minus 1 to the power m minus 1. So it is lambda minus 1 into lambda minus 1 to the power m minus 1, which will imply lambda into lambda minus 1 to the power of, here we just add m minus 1 plus 1. So that it is finally we will find out lambda into lambda minus 1 to the power of m. This shows that the theorem is true for n is equals to m plus 1. So this is the proof. So by mathematical induction, we can say that it is true for any n. So that we can say that the chromatic polynomial for a tree is lambda into lambda minus 1 to the power n minus 1 for all n. N is the total number of vertices. So these are the few theorems for the chromatic polynomial. In this video, we come to discuss about decomposition rule to find chromatic polynomial. In our last video, we come to know that how to find out the chromatic polynomial. But by using decomposition rule, it is much more easier to finding out the chromatic polynomial for any given graph. So, how to find out the chromatic polynomial? By using decomposition rule or decomposition principle. Let V1 and V2 be two non-adjacent vertices in a graph G. Let G dash be a graph obtained by adding an edge between V1 and V2. Let G double dash be another simple graph obtained from G by fusing the vertices V1 and V2 together and replacing sets of parallel edges with single edges. So what we will do initially? Let us do with an example, then we will understand better. Suppose any graph is given, this one. In this graph, we consider any two vertices, let it be V1 and V2, which are non-adjacent. We should consider only those vertices which are non-adjacent. So if this one is a given graph, then here V1 and V2, these two are the non-adjacent vertices which we can consider. Using these two vertices, we will create two graphs from this graph. First graph should be created by joining these two vertices which are not adjacent. That means this one, this is called the G dash. How to create this one? The same graph, only these two should be added because it is not added in the given graph. So in this way we create G dash. Again, G double dash should be created by merging these two vertices. These two are non-adjacent vertices. Now we create G double dash by merging these vertices V1 and V2. So if we merge V1 and V2, then what happens? So the edge V3, V2 should be merged with V3, V1 because now V1 and V2 have the same vertex. So if we do so, then V4 remains as it is, then V3 as it is, and for V1 and V2 should be merged, and accordingly these two edges should be merged, and these two, that means this one and this one, if coming to from V3 to V1, then these two are the parallel edges now. So instead of writing these parallel edges, we just consider any one edge. So finally, after joining these two, that means after merging these two vertices, we get this one as the graph. So this is our G double dash. So any graph is given, from there we find out which are the non-adjacent vertices. Any one pair we consider initially. After that, in the first step, we just add V1, V2. That means add these two adjacent, non-adjacent vertices by joining one edge, and we will create one graph that is called G dash. And by merging these two vertices, we will get another graph which is termed as G double dash. After doing this one, we will say our requirement for the chromatic graph of this graph. Our requirement is to find out the chromatic polynomial for this graph. So this is the notation for the chromatic polynomial, that is Pn G comma lambda. So it is n is the number of vertices, G is the given graph, and lambda is the polynomial in lambda. So this one we will find out by adding these two graphs, chromatic polynomial. So this one is the chromatic polynomial for this graph, and this one is the chromatic polynomial for this graph. Just look, in the G dash, the number of vertices are same as the G. But in G double dash, the number of vertex is one less than the G, because one vertex is merging in the another vertex. That's why we will write down in this way. This is our decomposition rule. So now, while we are going to find out the chromatic polynomial for any given graph, in this way we separate it into two graphs. After separating in this way, we will observe that this separated graph or these two created graph are complete graph or not. If they are not a complete graph, that means there is a provision to add more edges. That means there are more non-adjacent vertices present. So we again decompose further these two graphs and try to find out all the graphs as a complete graph, the decomposed graph as the complete graph. So if we look these two, then this one is a complete graph because 3 vertices, 3 edges, so this is a complete graph. but this is not yet a complete graph. So this one again we should decompose, and this decomposition should be like this one. From this one we have this V2 and V4. These two are the non-adjacent vertices. So in the next decomposition we should add V2 and V4. So we will find out G1 dashed, and again we should merge these two. If we merge these two, then what happens? V2 and V4 becomes now the same vertex. V2, V4 same vertex means V3, V4. This edge should be merging with V3, V2, and here the V1, V2, this edge V1, V4, this edge should be merging into the V1, V2. So that here after merging in this way, we will find out this one as the another decomposition, so that we will create these two graphs. So this is the, now look, this is a complete graph, this is a complete graph, and this one is also a complete graph. So finding out all those, what we will do, this one is decomposed again into these two. So this one means we can write the chromatic polynomial for this graph plus the chromatic polynomial for this graph. That is the chromatic polynomial for this one, and the plus of the chromatic polynomial for this one. Now, why we decompose it into the complete graph? That is because we know that the chromatic polynomial for a complete graph is very easy. If it is a third order, that is it is a graph with 3 vertices, then its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2. If there are 3 vertices. If there are 4 vertices, then here one more factor should be included. So in this way, we can find out the chromatic polynomial for any complete graph very easily. That's why we take this decomposition rule to convert a given graph into the different parts of the complete graph, so that we can find out the chromatic polynomial very easily. So this one is also called the fundamental recurrence theorem, fundamental reduction theorem. So we can say the recurrence terminates in a collection of complete graphs. So this is a recurring process. Once we decompose, then again if required we decompose. If these are not complete, then again we should go further for the decomposition. So this is a recurrence process, and this recurrence process will terminate while we collect all the complete graph. So in this way the decomposition rule will work. Now after decomposition, how to find out the chromatic polynomial? For that, with an example we should follow it. So using decomposition rule or decomposition theorem to find the chromatic polynomial of the following graph, we should have this following steps. So initially this one is the given graph, and that should be decomposed into these two parts. This is G dashed and G double dashed. We know how to decompose these two. According to these two non-adjacent vertices, we compose this one, and after adding these two or merging these two vertices, we find out this one. Similarly, as this one is not yet complete, so it should be decomposed further. So this further decomposition leads us to this graph. Here these two are the non-adjacent vertices, and depending upon that we will decompose these two. After this entire decomposition, what we will say, that the chromatic polynomial for the given graph should be equals to the chromatic polynomial for G dashed, that means this one, plus the chromatic polynomial for this one. But the chromatic polynomial for this one, that is this one, means it is the decomposition of these two, means these two. The chromatic polynomial for this one and the chromatic polynomial for this one. So finally we will find out that the chromatic polynomial of G is equals to this one plus this one plus this one. So we just substitute accordingly all. We will find out that the chromatic polynomial for this graph, this is a graph with 4 vertices and it is a complete graph. So its chromatic polynomial should be, it is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 plus of its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2. So that we have right here. And for this one also, it is a complete graph with 3 vertices and its chromatic polynomial is same as this graph. So that if you write down this one even, then we will find out this one. So these two are the same terms. So if we add these two, then we will find out 2 into this one. And from these two terms, we can take common delta lambda into lambda minus 1 into lambda minus 2. After taking this common, this part will be remaining, and from here it is the 2 only remaining. So if we simplify, we will find out this one leads us lambda minus 1. So if we multiply all those, then we will find out the lambda to the power 4 minus lambda 4 into lambda cube plus 5 into lambda square minus of 2 lambda, which is the chromatic polynomial for the given graph. We can verify that this is the chromatic polynomial or not. We know that this digit will verify that the how many number of edges are given in the given graph. So here it is the 4. So in our given graph, let us count that how many edges are given. So it is 1, 2, 3 and 4. So it is true. So this one is the chromatic polynomial. Anyway, so next here, if this one, suppose the graph is given for which we want to find out the chromatic polynomial, then we can do one thing, that we can do this one minus of this one. That also can be done. So this one, for if we want to find out the chromatic polynomial for this G dashed graph, then it should be find out by P4, that means the given graph G minus of this one. We just immediately calculate the chromatic polynomial for this graph. So this one, and the chromatic polynomial for this one, it is the chromatic polynomial, that is lambda into lambda minus 1 into lambda minus 2. So that if we write in this way, then we can find out the chromatic polynomial for this one directly. So now its chromatic polynomial, if we calculate, then we will find out that its chromatic polynomial is this one. And just observe here in this graph, the total number of edges are 1, 2, 3, 4, 5. So in the chromatic polynomial, this coefficient is 5 only. So this is the chromatic polynomial for that one. One more example, by using the decomposition rule, we are supposed to find out the chromatic polynomial for this one. So this one, again here we will find out that the non-adjacent vertices are present. So we should decompose it into two parts. So by this decomposition, so just look, if we consider these two vertices, then we should add in the first graph and we should merge these two vertices in the second graph. So after merging, we will find out this one as the graph. So both of them are non-complete graph. So that we should decompose further. So for this one, the non-adjacent vertices, now we can consider it is these two vertices. So that we have to add here. So we should add these two and we should merge in this second graph. So after merging these two vertices, if we merge, then we will find out this type of graph. Just look how to merge. This vertex will be merging here. So accordingly, this edge merging to this one, this edge merging to this one, and this edge merging to this one. So finally, we will get this one as the graph. For this one, it is again a non-complete graph, so that we should have these two as the non-adjacent vertices. So in the decomposition, we should add these two vertices by an edge, and after merging these two vertices, we will get this one as a graph. So now this one is a complete graph, this one is a complete graph. So further decomposition is not required for them. Here this one is a non-complete graph, and this one is again a non-complete graph. So that we go for the further decomposition. So now this decomposition means from here, the adjacent, these two vertices are non-adjacent. So we should add these two vertex by joining one edge. So after joining this one, now it becomes a complete graph. And after merging these two vertices, we will find out this one as a graph, which one is again a complete graph. For here, these two vertices are non-adjacent, so that we should join these two by an edge. And after joining this one, we will find out a graph which is a complete graph with 4 vertices. And by merging these two vertices, we will get this one, which one is again a complete graph with 3 vertices. So finally, we should add the polynomial for this one, plus the polynomial for this one, plus polynomial for this one, plus chromatic polynomial for this one, and plus these two. So 1, 2, 3, 4, 5 and 6. This total 6 graph for, we should add the chromatic polynomial. This one is a complete graph with 5 vertices. This one is a complete graph with 4 vertex. This one is also the complete graph with 4 vertex. This is a complete graph with 3 vertex. This is a complete graph with 4 vertex. And this is a complete graph with 3 vertex. So we have one complete graph with 5 vertex, total 2 complete graph with 4 vertex, and total 3 vertex with complete graph with 4 vertex, and total 2 graph with complete graph with the 3 vertex. So accordingly, if we add these 3, then we will find out the chromatic polynomial for the given graph should be this one. This is the chromatic polynomial with 5 vertex and a complete graph. There are 3 such graph with 4 vertices which are complete. So this one is of their chromatic polynomial, and 2 such graph with 3 vertices which are complete. So their chromatic polynomial is this one. So if we now simplify, then we will find out that we just take common lambda into lambda 1, lambda minus 1 into lambda minus 2 from all this, because everywhere it is common. So after taking common, we will find out this one, and after simplification we will get this one, and finally we will get this one as the chromatic polynomial. So this is a chromatic polynomial of G. Hence the chromatic number also we can find out from here. We will know that if we substitute the lambda values as 1, 2, 3, 4, then for which minimum value of lambda we will find out that the chromatic polynomial giving the non-zero value, then that particular lambda value is the chromatic number. Here we will find out that if we substitute lambda is equals to 3, then it is a non-zero value providing, so that the chromatic number for this given graph is 3, and this is the chromatic polynomial. So using this decomposition theorem, we can find the chromatic polynomial for the cycle and the wheel. In our last video, we will have that the chromatic polynomial of a cycle and a wheel. But how to prove that we will not have done over there. So the chromatic polynomial for the cycle is this one, and the chromatic polynomial for the wheel is this one. So these both of them can be proved by using the decomposition theorem. So if you know about the decomposition theorem properly, then you can easily prove these two formulas for the chromatic polynomial. So it is very obvious that for few standard graphs, we have the chromatic polynomial initially. Likewise, the complete graph, the null graph, the tree, the bipartite graph, and the cycle and the wheel. So if we have initially the known graph, then directly we can substitute the chromatic polynomial for those graphs. So okay, let us do one more example for this using decomposition theorem. So this one is a given graph, and our requirement is to find out the chromatic polynomial for this given graph. So just we observe initially the given graph. In this given graph, if this particular edge will be absent, then the graph becomes a tree. Is it not? So if this edge will not present, then it becomes a tree. And if it is a tree, then we know what is its chromatic polynomial, because any tree for, we know the chromatic polynomial is lambda into lambda minus 1 to the power of n minus 1, where n is the number of vertices in the tree. So what we should do? Here, instead of decomposing this one, what we will do? We consider the graph without this edge, so that the graph, let it be this one. Now we should decompose this one. So now if we decompose and we assume that these two are the two non-adjacent vertices, then its decomposition should be, if we add these two by an edge, then this one, and if we merge these two, then we will find out this one. So now look, our requirement is to find out the chromatic polynomial for this graph, so that we can find out by subtracting the chromatic polynomial of this graph minus of this graph. Now this one is a tree, so its chromatic polynomial is lambda into lambda minus 1 to the power 5 minus 1. 5 is the total number of vertices. But its chromatic polynomial is again unknown, because it is not a complete graph and it is not even a tree. So now what we can have for this graph, if this edge is not present, then it is again a tree. So that what we will do, for this one we consider and we decompose, then we will find out this one and this one. After merging these two vertices, we will get this one, and after adding by an edge, we will get this one. So this one and this one same, so that its chromatic polynomial should be this one minus this one, and this both are the tree now. So its chromatic polynomial is lambda into lambda minus 1 to the power 4 minus 1 because there are total 4 vertices given, and its chromatic polynomial is lambda into lambda minus 1 to the power 3 minus 1. 3 is the total number of vertices in this graph. So that we can find out the chromatic polynomial for this one, and that is this chromatic polynomial minus of this one. So we will get the chromatic polynomial for this one also. So now if we find out the chromatic polynomial for this one, then it should be this, the chromatic polynomial for this graph minus the chromatic polynomial for this graph. And after simplification we have done. So here is the calculation. So the chromatic polynomial for the given graph should be find out by means of this one minus of these two. So if we simplify, then we will find out it is lambda to the power 5 minus 5 into lambda to the power 4 plus 10 into lambda to the power 3 minus 9 into lambda square plus 3 of lambda. So from here we can easily say that the chromatic number for this given graph is 2, because if we substitute lambda is equals to 2, then it is a non-zero value providing. And one more thing, the number here, the coefficient for the second highest power of lambda is 5. So there should be 5 number of edges given in the graph. So let us check once more. How many edges are here? It is the total 5, and yes, it is 5. So just according to the polynomial, we can have the total number of vertices in the graph is 5 number. So hence this is the chromatic polynomial for the given graph. So I hope you understand and you enjoy the video, because I think it is my personal opinion that the chromatic polynomial, finding out the chromatic polynomial is much more easier by using the decomposition theorem. So for any graph you can find out the chromatic polynomial by using this decomposition theorem. If you use it properly and if you apply it is properly, then you can find it out very easily. So hope for the best. In this video lecture, we discuss some more theorems on chromatic polynomial. Till the previous videos, we have discussed the various things on the chromatic polynomial. We say that the chromatic polynomial have no constant terms. We say that the sum of the coefficient of the chromatic polynomial are always 0. And we say that the second highest coefficient always provides the total number of edges in the given graph, such and such. So all those things we are supposed to prove now. So the first proof is prove that the constant term of any chromatic polynomial of G is 0. So the constant term in any chromatic polynomial should be 0. So how to prove it? So let the chromatic polynomial of G is this one. This is a polynomial in lambda. So that is a general polynomial. So all the terms are there. So for any graph G, we know that the chromatic number is always either 1 or greater than 1. So for any graph G, here P and lambda should be 0. P and lambda means the chromatic polynomial of lambda should be 0 when the chromatic number is less than 1. This chromatic, that means the lambda value is when it is less than 1. Less than 1 means it is 0 when, then always whatever be the chromatic polynomials are there, that has to be 0. Because no such chromatic polynomials are there. So now in this polynomial, if we substitute lambda value as 0, then we will find out a0 into 0, a1 0, and all these 0, and the last an should be remaining. So that finally when we simplify, it will provide that an should be 0. So hence the constant term of any chromatic polynomial of G is 0 always. So hence the proof. So this is so simple, I think. So in the next one, the next theorem is prove that the sum of the coefficients of the chromatic polynomial of a graph G is always 0 if it contains at least one edge. A graph should have at least one edge. Then this theorem we should start to prove. So here let the chromatic polynomial of G is this one. Here constant term definitely not present, because in the previous theorem we proved that the constant terms are always 0. Now if G has at least one edge between a pair of vertices, then at least two colors are required to color the adjacent vertices. In a graph, only one edge given. One edge means it have two end vertices. So these two end vertices are the adjacent vertices because the edge is there. So for these two, we require at least two colors. So any graph, if you have with at least one edge, then we require at least two colors. So hence, the chromatic polynomial for the graph is 0 if we consider the chromatic, that is the lambda value is less than 2. So if we substitute lambda is equals to 0 or 1, then definitely we will find out the chromatic polynomial value is 0. So it is when lambda is equals to 1 from the polynomial, we will find out a0 1 to the power n. That means we substitute for all lambda it is 1. So if we substitute, then we will find out that total summation should be 0. That will implies a0 plus a1 plus a2 up to all these coefficient. This summation should be 0. So which will implies that the sum of the coefficients of the chromatic polynomial of a graph G is always 0 if it contains at least one edge. So this one is the proof of the theorem. So the next theorem prove that the coefficient of chromatic polynomial is alternate in sign. So any chromatic polynomial you will find out that the first term is positive, the second term is negative, the third term is positive, fourth term is negative, and so on. So the consecutive terms are always having the two different sign or the alternate signs are always there. So how to prove that? So for this proof, this problem can be proved by the method of mathematical induction depending on the number of edges E of the given graph G. If E is 0, that means no edges are there. No edges means it is a null graph. So if there are no edges given in a graph and total n number of vertices are there, then it should be a null graph with n number of vertices and its chromatic polynomial is lambda to the power n, that we know. So the result is true here because the coefficient of this polynomial is non-zero. So suppose that this is true for E number of edges. So we just assume that the theorem is true for E number of edges. So if B1 and B2 are two vertices in G which are adjacent, that means B1, B2, this one is an edge which exists in G. Again, we consider a subgraph by removing that particular edge which connecting the vertices B1, B2. So H is a subgraph of G where H definitely is a subgraph which is same as G but excluding this particular edge. So therefore, B1 and B2 must be non-adjacent vertices in H. That is very obvious. If we remove the edge from B1, B2, then B1, B2 are non-adjacent vertices and these are the part of H, the subgraph of G. So by decomposition theorem, we can have that for this subgraph H, if we find out the chromatic polynomial, then by decomposition process, what we will do? We just find out the G dash, that means the H dash, by adding the edge between the vertices B1 and B2. So this one is another one graph, and by merging the vertex B1, B2, we will get this another graph. Let this graph is in small h into H. So that one H plus this edge means it is the given graph G. So that instead of this one we can write this is the chromatic polynomial for G, the given graph, and this one. So from here we can write that this one is equals to PH lambda minus of this one. So that we can say that equation number 1. So now H is a graph with n vertices and E minus 1 edges. G is a graph with n vertices and E edges. And H definitely then is the subgraph of G with which have n vertices and E minus 1 edges. And HH, that means after merging the vertices V1, V2, this graph is with n minus 1 vertices, 1 vertex less, and let it is E1 edges containing, but definitely E1 is less than E. E is the total number of edges in G. So that is very obvious. Now what we will find out from the mathematical induction, that the chromatic polynomial for H then should be this one with n number of vertices. This one is the chromatic polynomial, that is the general chromatic polynomial with n number of vertices, and for this one the chromatic polynomial should be this one because here the one vertex is less, so that its chromatic polynomial should starts from lambda to the power n minus 1. here ai and bi, that means all these coefficients are positive integers according to our consideration. So hence from the equation number 1, I hope you can remember, this is our equation number 1. So from this equation number 1, now if we substitute these two values, then we will find out the first one for this one, and for the second one for it is minus of 1, then to the power n minus 1, then the remaining. So that what we will find out from here, so this is a polynomial, just substituting and simplifying. That is, look, if we just add, then what happens? This one is the individual term. Addition will be happen between these two terms. Then next addition will be happen between these two terms. Next, in this way, the addition will happen. So after adding these two polynomials, that means subtraction of these two polynomials, we will get this one. So this is again a polynomial which contains the coefficients which are in alternate in sign. Just observe, these are in alternate in sign. So which proves the theorem. And one more theorem corresponding to this chromatic polynomial is, so that the absolute value of the second coefficient, that is the coefficient of lambda to the power n minus 1 in the chromatic polynomial of a given graph equals the number of the edges in the graph. So that always I am telling you that the coefficient of lambda to the power n minus 1 implies the total number of edges given in the given graph. But how it will be possible, that we are going to prove now. So for that, this problem can be proved by the mathematical induction again. So depending upon the number of edges. So if e is equals to 0, then obviously the chromatic polynomial is lambda to the power n, where n is the number of vertices in G, and this is for the null graph. Hence the coefficient of lambda to the power n minus 1 in this polynomial has to be 0. So the result is true when e is equals to 0. Next, if it is, we know that from the previous theorem that P of, that is the chromatic polynomial of G, is equals to chromatic polynomial of H minus of chromatic polynomial of small h into H. So since H is a graph with n vertices and E minus 1 edges, therefore by induction hypothesis, the coefficient of lambda to the power n minus 1 should be minus of e to the power minus 1. I hope you understand. The H is the graph with n vertices and e minus 1 edges. And according to the mathematical induction hypothesis, then it should be proved that the coefficient of lambda to the power n minus 1 in the given polynomial should be minus of e to the power e minus 1, because the second term is always negative, that we have that we observed always. Again, the coefficient of lambda to the power n minus 1 in HH should be 1. Because here one vertex is lesser and the first term is lambda to the power n minus 1, and for the first term its coefficient is 1. So since HH have n minus 1 number of vertices, that's why we will do this one. Hence the coefficient, the total coefficient in the given, the total coefficient of lambda to the power n minus 1 for the graph G should be then what it is. According to this formula, the coefficient of lambda to the power n minus 1 from here, and the coefficient for lambda to the power n minus 1 from here, and these two should be subtracted. So that it should be, for the first it is minus of e minus 1, and for the second it is 1. So minus of 1. That's why if we calculate, then it is minus of e. So which is the absolute value always we consider as per the number of edges. So hence the result is proved that always the number of edges should implies the second coefficient in the chromatic polynomial. Second coefficient means it is the coefficient of lambda to the power n minus 1. So all those with for example we can say again that suppose this one is a given graph and its chromatic polynomial is very easy, that we know it is lambda into lambda minus 1 into lambda minus 2, and its simplification form is this one. So from here we can say no constant term exists over here. Total 3 vertices are there because the highest power is 3. Total 3 edges are there because the absolute value for the second coefficient is 3. And the coefficient of the polynomial are alternate in sign. So look, it is first positive, negative, positive. So the coefficient of the polynomial are alternate in sign. And the sum of the coefficient here it is the 1, it is minus 3 and 2. If we add all these 3, then it is 0. So always it will happen. And the final thing which we can say, the chromatic number for this given graph is 3. That is because if we substitute lambda is equals to 1 here, then it gives us the value 0. For lambda 2, again it gives us the value 0. And when we substitute lambda is equals to 3, then it is a non-zero value providing. Hence, we can say the chromatic number for this given graph is 3. So, if we have the chromatic polynomial for a graph, then we can find out, or we can have analyze all those things from the chromatic polynomial only for a given graph. Now it is the time for solving the problems on chromatic polynomial. So the first problem is, find the chromatic polynomial and chromatic number of the given graph G. So this one is our given graph. Initially, whatever be the graph is given, we should observe the graph very carefully. The given graph is a tree, and this graph having how many vertices? 1, 2, 3, 4, 5, 6, 7 and 8. And the graph having 8 number of vertices. So if it is so, we know that for a tree, the chromatic polynomial is lambda into lambda minus 1 to the power n minus 1. In the given graph, it is a tree with the 8 number of vertices. Hence, its chromatic polynomial should be P8 lambda is equals to lambda into lambda minus 1 to the power 8 minus 1, that is lambda into lambda minus 1 to the power of 7. So this is the chromatic polynomial. It is so simple. Since P8 lambda is equals to 0, for lambda is equals to 0, and it is again 0. If we substitute lambda is equals to 1, then we substitute lambda is equals to 2, then we will find out P8 lambda is not equals to 0. So we can say the chromatic number for this graph is 2. Next, it is the second question, and the question is, find the chromatic polynomial and the chromatic number of the graph, this one. So this one is a given graph, and we are supposed to find out the chromatic polynomial for this one and then the chromatic number also. So just look, this one is not a connected graph. Till that, whatever the graph we are dealing with, all are connected graph. But here the given graph is a disconnected graph. So disconnected graph having two components. So each component we can say as the individual graph. So the first component we say the graph G1, and the second component, let us say it is G2. So for the first graph, that is the first component if we consider, then it is a complete graph with 4 vertices. And similarly the second component, again it is a complete graph with 3 vertices. We know what are the chromatic polynomials for the complete graph. So just simply we just write down the chromatic polynomial for G1 should be this one, which is the chromatic polynomial for a graph with 4 vertices, which is a complete graph. So it should be lambda into lambda minus 1 into lambda minus 2 into lambda minus 3. And similarly the chromatic polynomial for the second component should be this one. So hence, by principle of counting, we say that the chromatic polynomial of the given graph G, the entire graph G, should be in the entire graph total 7 vertices are there. So we should write P7G. So that should be the chromatic polynomial for G1 into the chromatic polynomial of G2. So this is for the chromatic polynomial of G1, and this is the chromatic polynomial for G2. If we multiply these two, then we will find out the chromatic polynomial. And obviously, if we are going to find out the chromatic number, then from here we can find out that if we substitute lambda is equals to 1, then it should be 0. Lambda for 2, it should be 0. Lambda for 3, again it should be 0. If we substitute lambda is equals to 4, then only we get this one, this value is non-zero. Hence, the chromatic number for this given graph should be 4. So in this way, we can find out the chromatic polynomial and the chromatic number. So I hope it is so very simple. Next one, the next question is that how many ways are there in a tree with 4 vertices which can be colored with at most 3 colors. So just let me tell you the question again. How many ways a tree with 4 vertices can be colored with at most 3 colors? So first of all, the given graph is a tree with 4 vertices. and its chromatic polynomial, we know that should be lambda into lambda minus 1 to the power n minus 1. So here the lambda value is given, that the total number of colors used, it is given 3, and the number of vertices given 4. So that if we substitute lambda is equals to 3 and n is equals to 4 in this chromatic polynomial of a tree, then we will find the total value is 24. So which solves the problem. So I hope it is super easy. Next one, it is a tree can be colored with at most 4 colors in 324 different ways. Find the number of vertices in the tree. Now it is given that how many colors are there and how many total different ways are there by which we can color the tree. This time we are supposed to find out the number of vertices in the tree. Again the same process. This is the chromatic polynomial for the tree, and here if we substitute lambda is equals to 4 and the total value when we substitute lambda is equals to 4, then it is given as 324. So if we substitute and just simplify, how to simplify? After some substitution, we just take the LCM of 324. So this is the LCM. So according to this LCM, we can write that it is 4 into 3 to the power 4, and here we will find out 4 into 3 to the power n minus 1. So if we compare both sides, then we will find out n minus 1 should be equals to 4, which will implies that n is equals to 5, which is the total number of vertices. I hope it is very simple to find it out. So now the next one. So the next question is a polynomial lambda to the power 3 minus 3 into lambda square plus 2 lambda plus 3 is a chromatic polynomial of a graph G. This is given. So justify your answer. So this polynomial, this given polynomial is a chromatic polynomial or not, that we are supposed to justify. So just observe it again very carefully and we will find out there exists a constant term. As there exists a constant term, so without any further calculation, we just say that the given polynomial is not at all a chromatic polynomial for any graph, because we know that any chromatic polynomial cannot contain the constant term in the polynomial. So that it is not a chromatic polynomial for any given graph. Now the next one more problem is here, and the problem is prove that this one cannot be the chromatic polynomial of any graph. So we are supposed to prove that this given graph is not a chromatic polynomial for any given graph. So first of all, we observe the polynomial carefully. Here constant term does not exist. The coefficients are alternate in sign. So that we now proceed further. So the given, suppose this one is the chromatic polynomial for a graph G. So according to this one, highest power of lambda is 4. So that we can say the total number of vertices in the graph should be 4. Again, the coefficient of the second highest is the new absolute coefficient, it is 3. So the graph should have 3 number of edges. So that a graph having 4 vertices and 3 edges, if we want to draw, then there are two possibilities actually. Either it is connected or it is disconnected. If the graph is connected, then it should be a tree, because this is, we can say in our case 1 is here n is equals to 4 and a is equals to 3. So number of vertices is 4 and age is the one less than the number of vertices, that is n minus 1. So that property follows for the tree. So if that is 4 number of vertices and 3 number of edges are there, then it should be a tree. So as it is a tree, then its chromatic polynomial should be lambda of lambda minus 1 to the power n minus 1. Here n is equals to 4. So it should be lambda into lambda minus 1 to the power of 3. If we simplify, then we will find out this one as its chromatic polynomial, which is completely different from the given chromatic polynomial. Hence, the given chromatic polynomial is not a chromatic polynomial for any tree having 4 vertices and 3 edges. Now the case 2. In case 2, we can have that the graph is a disconnected graph. If it is a disconnected graph having 4 vertices and 3 edges, then it have the only possibility is this one. So if it is so, then here the two components we will find out. So this is the first component, say G1, this is the second component, say G2. both are the complete graph. Here the complete graph with 3 vertices and this is the complete graph with only 1 vertex. So accordingly, we have the chromatic polynomial for this one is lambda into lambda minus 1 into lambda minus 2. And for this one, its chromatic polynomial is only lambda because it is a null graph we can treat as. So that if we multiply these two, then we will find out this one. Now if we compare with the given chromatic polynomial, then again these two are different. Hence this is not a chromatic polynomial for any disconnected graph also. So if any such type of problems are given, then we should go for all type of possibilities and we explain accordingly to show that the given chromatic polynomial is actually a chromatic polynomial for any given graph or not. So here we will find out this chromatic polynomial is not a chromatic polynomial for any graph. So that's all for this video. I hope you like the problems which I have solving here. I'm requesting you all, if you have any other problems, then you should send it to me in the comment box. And if you have any query, then also you can ask me regarding your problems. And if you like my video, then now please do subscribe and like my channel. In this video lecture, we are going to discuss some more problems on chromatic polynomial. Especially in this video, we are going to discuss to calculate the chromatic polynomial of any given graph by using two different methods. One method which we discussed in our previous lecture, that is the decomposition method, and another one is the simple permutation and combination method. So now the first problem is given here, this one. Find the chromatic polynomial of the given graph, this one. This one is a bipartite graph with 2 vertices in one side and 3 vertices in another side. So this one is the given graph. Since the graph has 5 vertices, therefore the chromatic polynomial of the given graph is this one that we will find out from the first lecture on the chromatic polynomial. So if we expand this one, then we will find out its polynomial as this one. Here we are supposed to find out the values C1, C2, C3, C4 and C5. We know that the chromatic number of any bipartite graph is 2. This one given a bipartite graph and we know that the chromatic number of any bipartite graph is 2. So that from there we can say C1 definitely be 0. Now the C2. For C2 it should be exactly 2 colors are required to color the given graph. So here it is the 2 factorial, that is out of 2 colors if we want to take 2 colors. C2 means here I should be taken as 2. So out of 2 colors if we want to choose any 2 colors, then it is possible only in 2 factorial ways. Now for the 3 colors, if out of 3 colors, here how to get the colors? Suppose 3 now colors we have. Out among these 3 colors, 2 vertices should be given 2 different colors. So now the third vertex, to what to do? Here the third vertex we have the 2 alternatives to give the color. For this vertex also we have the 2 more possible way to give the color, but this one for we remain only 1 more way to give the color. So accordingly we will find out that C3 is 3P2, that means out of 3 we have to choose any 2 or we have to select in fact any 2, and 2 color for the next vertex and 2 more color for the 1 more vertex and 1 more for the 1 more vertex. So if we simplify this one, then it will be 24. Now corresponding to this C4, C4 means out of 4 colors. So out of 4 colors initially we have to take the 2 colors, any 2 colors for here. So out of 4 colors we should take any 2 colors here. Now for this one we have again the 2 different, and here for 2 different and here for total 2 different choices we have. So that accordingly we will find out that C4 is this one. And C5 is always, it is the 5 factorial. So it is 120. Now if we substitute the values of C1, C2, C3, C4 and C5, all these values, then we will find out the polynomial in this way. And if we simplify, then we will get the chromatic polynomial as this one. So this is one of the way to find out the chromatic polynomial. But for the same graph, if we use the decomposition method, then it becomes much more easier. At least for me, it is much more easier if I use the decomposition method. So that the second possibility to find out the chromatic polynomial for the same given graph is, here the given graph is this one. Just have a look. So this one is our given graph. So from this given graph, how to find out the chromatic polynomial? So for that, what we will do? We just simply So for this given graph, the second method is by using the decomposition method. So our given graph is this one. So from this given graph, if we want to find out the chromatic polynomial using the decomposition method, then at first if we observe this graph, then we will find out if we want to make this graph complete, total 5 vertices are there. With 5 vertices, if we want to make it a complete graph, then we require total n into n minus 1 by 2. That means 5 into 5 minus 1, that means 4 here. So by 2 means total 10 number of edges. Here total 6 edges are given, so that we are supposed to introduce 4 steps here to get the decomposed here. So that instead of that, if we remove 2 edges from here, then it becomes a tree. So that we can think of a reverse decomposition method. So that initially this one is a given graph, but we consider a graph G as this one, which is a tree. Now if we decompose this one using these two as the non-adjacent vertices, so we should add initially these two, so that we will get this one, this is the G dash, and after that if we merge these two, then we will find out this graph. So that if we will get in this way, so this one is the graph whose chromatic polynomial we don't know. This one again a graph whose chromatic polynomial we don't know. But this one, as it is a tree with 5 vertices, so its chromatic polynomial is known to us. Now for this one, we again go for the decomposition. So for this one, if we decompose, then here these two are the non-adjacent vertices. So if we join these two, then we will find out this graph, and if we merge these two, then we will find out this one, this graph. So this one is our given graph, which for we are supposed to find out the chromatic polynomial. Now for this one, we should find out the chromatic polynomial, and this one should be calculated on the basis of these two. So next what to do, we should find out the chromatic polynomial for this one, or we just going to decompose this one, because if we add these two, then it becomes complete. So accordingly, this one for we will get these two decompositions, and for this one again, if we join these two vertices, then it becomes the complete graph. So that accordingly, we decompose this one into this part. One more thing, here if we do this one, so after this one, still these two are the non-adjacent vertices. So for that, we have to decompose it once more. So finally, in this way, by decomposition, we will find out the chromatic polynomial for this graph is the summation for this one, and this one. This is a complete graph with 4 vertices. This one is a complete graph with 3 vertices, and this one is also the complete graph with 3 vertices. And for all, we know the chromatic polynomial, so that we can find out the chromatic polynomial for this one very easily. Similarly, for this one also we can find out the chromatic polynomial very easily, because this one is a complete graph with 4 vertices and this one is a complete graph with 3 vertices. If we add these two, then we will find out the chromatic polynomial for this one. So after getting the chromatic polynomial for these two, now we can find out the chromatic polynomial for this one by subtracting this one with this one. So after getting this one, we will get the chromatic polynomial for this one. And if we substitute this value here and this one, we have already calculated the chromatic polynomial. So if we subtract these two, then we will find out the chromatic polynomial for this graph, which is our desired graph. So accordingly, if we substitute the values here, then we will find out that first of all, we calculate the chromatic polynomial for these two graphs. At first, we find out the chromatic polynomial for this one, and this one. So according to our calculation, for this one the chromatic polynomial, for this one the chromatic polynomial is the summation of this one plus this one plus this one. So it is this one plus 2 into this one, because there are one complete graph with 4 vertex and 2 complete graph with 3 vertex. If we simplify, then we will find out it as lambda into lambda minus 1 its whole square into lambda minus 2. Again similarly, if you find out the chromatic polynomial for this one, then it is lambda into lambda minus 1 into lambda minus 2 its whole square. Now the chromatic polynomial for this graph, for we should find out it by the subtracting the chromatic polynomial of this one minus of this one. We have calculated the chromatic polynomial of this one, and its chromatic polynomial is lambda into lambda minus 1 to the power 4. So that we do the same thing. So after simplification, we will find out the chromatic polynomial like this one. And now finally the chromatic polynomial for this one means it is the subtraction of this graph minus of this graph. So accordingly, if we do so and simplify, then we will find out the chromatic polynomial of this graph is this one. So this is the simplification. Just look at the simplification and you will calculate by yourself, so that you will find out the same thing you are getting or not. So just look, by the previous method, when we find out the chromatic polynomial for this graph, then its chromatic polynomial we have calculated as it is lambda into lambda minus 1 into lambda cube minus 5 lambda square plus 10 lambda minus of 7. And here also we will get the same value. So after simplification of this one, we will get the same as like this one. So by both the method, we will get the same chromatic polynomial, and that has to be. Let us do one more example so that we can understand it much better. So one more example, for let us consider this graph, and for this graph we are supposed to find out the chromatic polynomial. So at first we are going to use the first method. So according to the first method, here total number of vertices are 5. So with the 5 vertices, this one is our chromatic polynomial, just like the previous one. Just have a look. P5 lambda is C1 into lambda C1 plus C2 into lambda C2, in this way up to P5 of this one. So now if we just simplify, that means our next target is to find out the value of C1, C2, C3, C4 and C5. So in the given graph G, 3 different colors are required for the triangle, as this graph contains a triangle. So at least 3 colors should be required. So accordingly, we can say C1 should be 0, C2 should be 0, and the highest one should be the 5 factorial. That always happens. Now our target is to find out C3 and C4 more. For C3, 3 different colors can be assigned to the vertices here V2, V3 and V4. In this graph, in the vertex V2, V3, V4, we initially assign the 3 different colors. So that 3 different colors can be assigned in 3 factorial ways. So that is the 6 different ways are there to assign the 3 colors for these 3 vertices. Now the vertices V1 and V5. Now it is V1 and V5 we are supposed to put the color. So this V1 and V5 can be colored with only this one, as V1 is connected with V3 and V2 both. So only V4, this color can be given to the vertex V1, and similarly for V5 only the color of V2 can be given. So only one way is there to give the color to V1 and one way is left to give the color at V5. So that total colors with 3 different colors we can color in this graph is total 6, that is 3 factorial. So that this value, that is the C3, is 6. Now to find C4, among 4 different colors, 3 can be chosen by 3 different ways, that is 24 ways for the vertices V2, V3 and V4. Now the 4th color can be assigned to any of the vertex V1 and V5. So there are 2 choices left for the vertex V1 and no choice for the 5th vertex. So that the total different number of colors we can choose, or total different number of ways to choose the colors with 4 different colors is, it is 48. So now after getting this one, here if we substitute these values of C1, C2, C3, C4 and C5 in the polynomial, then we will find out. Just look, we substitute for C3. Here it is 6. For C4 it is 48 and for C5 it is 120. So after that, when we simplify, then we will find out this one is the chromatic polynomial. And from here it is definite that the chromatic number is 3. So this is the one of the way by which we can find out the chromatic polynomial. Now we are discussing about the second method. So the graph is this one, and this graph can be decomposed in this way. This one is the graph. So initially we will find out that these two are the two non-adjacent vertices. So accordingly, if we will decompose it, then it is the first graph and this is the second graph after merging these two vertices. So now look, no one is the complete graph. So that the second step for we should forward. Now if we merge these two, that means we just add these two vertices, then we will get the one more vertex, and after merging these two we will get this one. So now this is a complete graph with 5 vertices and this is also a complete graph with 4 vertices. And for this one we should merge these two vertices, so accordingly we will get this one. This is a graph with 4 vertices and it is a complete graph. And by merging these two vertices we will get this graph, and this one is a complete graph with 3 vertices. So now look, after this one is a given graph and we should go for the decomposition. So the final, these are all are the complete graph. So we should stop our decomposition here. So finally, if we add the chromatic number of these 4, then we will get the desired chromatic polynomial for the given graph. As this one is a complete graph with 5 vertices, so its chromatic polynomial is this one. These two are the same graph. So there are 2 such graphs. So its chromatic polynomial is this one. And for this one, a graph with 3 vertices, a complete graph, its chromatic polynomial is this one. So if we merge these 3, then we will find out, if we take common lambda, lambda minus 1, lambda minus 2 from all these 3, and after simplification, we will get this step. Just have a look. So that finally, we will find out the chromatic polynomial as lambda to the power 5 minus 8 lambda to the power 4 plus 24 lambda to the power 3 minus 31 lambda square plus of 14 lambda. So in this graph, just have a look. Total number of edges are 1, 2, 3, 4, 5, 6, 7 and 8. And in the chromatic polynomial, we will find out this number is 8. So that it is the chromatic polynomial for the given graph. So the same graph and 2 methods, both the methods are effective and easy. Which method you think is easy for you, you should go for the method. And this is the way to solve the chromatic polynomial, that means to find out the chromatic polynomial for a given graph. So that's all for the chromatic polynomial. This video is about to solve those problems which are provided to you. So before starting that one, I must say thank you to all of you for your honest and sincere attempt. At least you have tried to solve all those problems. Many of you have given the right answer, but most of the you peoples are still not understand the process properly, I think. So for all of you, there is the video where I am solving all those problems which I have provided to you previously. So the first problem is this one. In this graph, total 5 vertices are given. And we should observe this graph very carefully. So this one is not a complete graph. For this graph, we are going to find out the chromatic polynomial using decomposition method. So this one is not a complete graph because this vertex having degree 2. It should have degree 4. Then we can say this one is complete. So while we are going to make it complete graph, so that 2 edges should be connected with this one, and that 2 edges should be connected, one from this one and another should be connected from this one, because these 2 vertices are of degree 3 and the remaining these 2 vertices are of degree 4. So now initially let us choose this one and this one, these 2 vertices. So if we add these 2 vertices by an edge, so that we will get this one as the graph, and the next part is by merging these two vertices. That means if we merge these two vertices, then while we are going to merging these two vertices, then these two edges will be coincides with these two, so that we will find out this one is the graph, which is a complete graph with 4 vertices. Now this graph, if we emphasize on, so then this one is not yet a complete graph. So for that we should find out which edge should be introduced here. That means which two vertices are not adjacent still. So we will find out that these two vertices are non-adjacent. So in the next step, we should add these two vertices by joining one edge. So that after joining these two vertices by an edge, at the next part we should merge these two vertices. So if we merge these two vertices, then we again get this one is a graph which is a complete graph with 4 vertices. Now if we observe this graph carefully, then we will find out now this one is a complete graph with 5 vertices. Just look, this vertex having degree 4, this vertex having degree 4, this vertex also having degree 4, this vertex having degree 4, and this one is 2 having degree 4. So all the vertices are having degree 4 and total 5 vertices are there. So it is a complete graph. So for the complete graph, we know its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 into lambda minus 4. That we know. So this one with, we should add this one, and not only that, this one plus this one gives the chromatic polynomial for this graph. And with that, if we add this one, then we will find out the chromatic polynomial for this graph. So here we will find out, we are supposed to add a graph which is a complete graph with 5 vertex, and we should add 2 graphs which is a complete graph with 4 vertices. So a complete graph with 4 vertices for the chromatic polynomial is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3. So here 2 such graphs are there. That's why this 2 should be included here. So now if we add these 2, then we will find out this one as our chromatic polynomial. Just by simplification, we will find out this one is our chromatic polynomial, and its expanded form is this one. In this chromatic polynomial, we observe that the second coefficient, the numerical value for the second coefficient is 8. That is the total number of edges in the given graph. Just check. This one is the graph, and how many edges are there? 1, 2, 3, then 4, 5, 6, 7 and 8. These are the total 8 edges are here in this graph. That's why this one is the chromatic polynomial for the given graph. And from this chromatic polynomial, we can say the chromatic number for this graph is 4. Because chromatic number 4, we just observe this chromatic polynomial, and if we substitute lambda is equals to 1, then it gives us the 0 value. For lambda 2 also it will gives us the 0 value. For lambda 3, it is again providing us the 0 value. When we substitute lambda is equals to 4, then this one becomes non-zero. Hence the chromatic number for this given graph is 4. So this is our first problem. So this is the chromatic polynomial, this is the factorization form, and this is the expanded polynomial form of the chromatic polynomial, and this is the chromatic number. Now the second problem. So the second problem is this one. This one is the given graph. So for this graph, we are supposed to find out the chromatic polynomial. So just at first, we should observe the graph very carefully. After observing the graph, we have a feel that the graph is more tending to the tree. So it is much more comparable with a tree. So that what we will do, we initially consider a graph having without this edge. That means we just consider this graph. So this one is a tree. Now if we apply the decomposition rule, then these two are the adjacent vertices, so that we should add these two vertices by an edge. So in the first part it should be added, and in the second part these two vertices should be merged. If we merging these two vertices, then we will find out this one is the graph. So this one is a tree, this one is a tree. This tree having the total 7 vertices and this tree having the 6 vertices. We know what is the chromatic polynomial for a tree. So that our requirement is the chromatic polynomial for this graph, because this is our given graph. So its chromatic polynomial is here this one, the chromatic polynomial for this graph minus the chromatic polynomial for this graph. So if we will do so, then it is lambda into lambda minus 1 to the power 7 minus 1, that is 6. And for this graph, the chromatic polynomial is lambda into lambda minus 1 to the power of 5. So this one is the chromatic polynomial for these two. So we should subtract this one from this one, and after simplification we will find out this one. This is a chromatic polynomial for the given graph, this one, and its expanded form is this one. Now its chromatic number is 3, because if we have this one as a chromatic polynomial, then we will find out that for lambda is equals to 3, we will find out a non-zero value. So that the given graph for the chromatic number is 3, and these are the chromatic polynomial. Here one more thing, you should observe that this second coefficient is 7, that is the total number of edges given in the graph. So just count the number of edges. This is 1, 2, 3, 4, 5, 6 and 7. So total 7 number of edges are here. So this is the chromatic polynomial for the given graph. Now the next graph is this one. We are supposed to find out the chromatic polynomial for this graph. So this graph is again very much tending towards a tree. So this is almost towards a tree. So what we will do, initially we start from this graph. So at first we should draw a graph like this one. So this one is a graph we consider, and here we should add these two vertices. So by this one we should add, and in the next step we should merge these two vertices. So after merging these two vertices, we will find out this graph. Just have a look. So after merging these two, we will find out this one as the graph, is it not? So these are the two things. Now our requirement is the chromatic polynomial for this one. So that should be finding out by subtracting the chromatic polynomial of this graph minus the chromatic polynomial of this graph. This one is a tree. So its chromatic polynomial is very simple. But this one is not a tree. So for this graph, we should find out the chromatic polynomial, because it is neither a tree nor a complete graph. So now we should think of that the graph is this one. So now if we apply the decomposition rule on this graph, then we should add these two vertices. So after adding these two vertices, what we will find out here? So this one is the graph. So we should add this edge. So now look, these two are the same graph, and after merging these two vertices, we will find out the graph like this one. So this one is the graph. So that now this one is a tree and this one is also a tree. So for this graph, the chromatic polynomial is the chromatic polynomial of this tree minus the chromatic polynomial of this tree. This is a tree with 5 vertex and this one is a tree with 4 vertex. And after getting this chromatic polynomial of this graph, for this graph, while we are going to find out the chromatic polynomial, then it is the subtraction of the chromatic polynomial of this tree minus the chromatic polynomial of this graph. So that its chromatic polynomial, while we are going to calculate, then it is this one, and its chromatic polynomial is, as there are total 6 number of vertices, then it is lambda into lambda minus 1 to the power 6 minus 1, that is 5. Then minus of the chromatic polynomial of this one. So its chromatic polynomial is again the chromatic polynomial for this graph minus this graph, that is lambda into lambda minus 1 to the power 4 minus lambda of lambda into lambda minus 1 to the power of 3. So now if we simplify, then we will find out that its chromatic polynomial is lambda into lambda minus 1 to the power 3 into lambda square minus 3 lambda plus 3, and its expanded form is this one. So it is very clear that its chromatic number is 2, because if we substitute the lambda is equals to 2, then we will find out the non-zero value of this chromatic polynomial. So here the second coefficient is 6, so that we can say that the given graph contains total 6 number of edges. Just have a look, 1, 2, 3, 4, 5 and 6. So there are total 6 number of edges are there. So this is the chromatic polynomial for this given graph. Now the next problem. So the next problem is now this one. So this one is the given graph. For this graph, again, when we are going to find out the chromatic polynomial, then again we compare this graph with a tree. If this edge is not there, then it becomes a tree. So that let us start with this graph. This one is a given graph having the same number of vertices, and we decompose it. So while we decompose, we should add these two vertices first, then it becomes our given graph. That means our required for which graph we are supposed to calculate the chromatic polynomial, that graph we will find out. And after merging these two vertices, we will find out this graph. This one is a tree, this one is a tree. So if we subtract the chromatic polynomial of this graph minus the chromatic polynomial of this graph, then we will find out the required chromatic polynomial. So if we will do so, then it is the chromatic polynomial for given graph. Its chromatic polynomial is lambda into lambda minus 1 to the power 4, and its chromatic polynomial is lambda into lambda minus 1 to the power 3. If we substitute and simplify, then we will find out its chromatic polynomial is lambda into lambda minus 1 to the power 3 into lambda minus 2, and its expanded form is this one. Here the second coefficient is 5. That means in the given graph total 5 number of edges are there, and that we can observe very carefully that 1, 2, 3, 4 and 5, these are the total number of edges given. And the chromatic polynomial, I hope you can say now, yes, it is 3, because if we substitute lambda is equals to 3, then the graph having that chromatic polynomial is non-zero value. That's why the chromatic number is 3 for this graph. Now one more extended form of the above graph is this one. In previously these two are joined. Now there is one more vertex given, and this one is joined accordingly. So for this one, if we want to find out the chromatic polynomial, then again we think of that this one becomes a tree if this edge is not there. So that we start from this graph. Now if we apply the decomposition rule here, then we should add these two vertices which are non-adjacent. So after adding these two, we should merge these two vertices. If we merging this vertex, then we will get this graph. And this one is nothing but the previous problem. Is it now? So that what we will do, we will now, if we find out the chromatic polynomial for this graph, then it should be the chromatic polynomial of this graph, which is a tree, minus of the chromatic polynomial of this graph. In just previous problem, we will find out its chromatic polynomial. So it is the chromatic polynomial for this graph, that tree is lambda into lambda minus 1 to the power 5, because there are total 6 number of vertices, and minus of the chromatic polynomial of this graph, which is we will find out lambda into lambda minus 1 to the power 3 into lambda minus 2. So if we just substitute all those, then we will find out this one. So after simplification, what we will find out here? After simplification, we will find out the chromatic polynomial for this graph is lambda into lambda minus 1 to the power 3 into lambda square minus 3 lambda plus 3. And its expanded form is this one. Here the second coefficient is 6, which will implies that total 6 number of edges are there. And its chromatic number is, I hope you can say, yes, it is 2. Because if we substitute 2 here, then we will find out it provides a non-zero value. So its chromatic number is 2. One more problem is this one. In this graph, again total 5 number of vertices are given, and it is definitely not a complete graph because these two vertices are non-adjacent vertices. So if we decompose this one and apply the decomposition rule, then we should add these two vertices by an edge, and we should merge these two vertices. So while we are merging, then we will find out this graph, because if we merge this one to this one, then you just observe these all 3 edges should be merged accordingly, and we will find out this graph. This one is a complete graph with 4 vertices, and look, this one is a complete graph with 5 vertices. So we know the chromatic polynomial for a complete graph quite well. So if we substitute the chromatic polynomial for this graph, it is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3 into lambda minus 4, and its chromatic polynomial is up to lambda minus 3. So if we simplify, then we will find out lambda into lambda minus 1 into lambda minus 2 into lambda minus 3, its whole square is the chromatic polynomial, and its expanded form is this one, and its chromatic number is 4, because if we substitute the lambda is equals to 4, then only we get the non-zero value for this chromatic polynomial. So one more example of the same kind. So if we have this one as a graph, then what should be its chromatic polynomial? If we remove any one edge from here, then we can say it is a tree. So that what we will do, we should start from this graph. So we should start from this graph. So this one is a graph, and suppose this edge is not there. So what we will do, in the decomposition rule, we should add this edge here. So that means we just add these two vertices which are non-adjacent. and its counterpart means we should merge these two vertices. So if we merge these two vertices, then we will find out the graph of this one. So this one is the graph which we will find out. So look, this one is the graph which we will find out. Now our requirement is the chromatic polynomial for this one. So its chromatic polynomial means the chromatic polynomial for this graph minus the chromatic polynomial for this graph. Its chromatic polynomial is known because it is a tree, but its chromatic polynomial is not known because it is not yet a complete graph. So, but it is again almost like a tree. If we remove this edge, then it becomes a tree. So let us do this one. So this one, let us consider this one is a graph which is a tree, and we now apply the decomposition rule. So if we apply the decomposition rule, then we should add these two vertices, then the graph becomes this one. Is it now? So then the graph becomes this one. So this is, and its counterpart, we should merging these two vertices. If we merge these two vertices, then it is this graph, which is a complete graph with 3 vertices. Now its chromatic polynomial means the chromatic polynomial for this one, which is a chromatic polynomial of a tree, that is lambda into lambda minus 1 to the power 3, because total 4 number of vertices are here, minus of the chromatic polynomial of this one, which is a complete graph. So its chromatic polynomial is lambda into lambda minus 1 into lambda minus 2. So we can find out the chromatic polynomial for this one. After getting the chromatic polynomial of this one, we can easily find out the chromatic polynomial of this one, because now it is this one minus of this one. So the same thing when we will do, then just the chromatic polynomial for this one is this one, chromatic polynomial for this one is this one, and the chromatic polynomial for this one is this one. While we solve, we will find out it is lambda into lambda minus 1 into lambda minus 2 into lambda square minus 2 lambda plus 2. And its expanded form is this one. So that its second coefficient is 5. We can say in the given graph, total 5 number of edges are there. Just have a look. 1, 2, 3, 4 and 5. And its chromatic number is, yes, it is 3. Because if we substitute lambda is equals to 3, then it is the providing non-zero value. So in this way, we can solve all those problems. I hope now you can able to solve all those problems. Not only these, but whatever the graphs are given, just emphasize on the graph, observe the graph very carefully, and accordingly you should set your steps to solve the graph to find out the chromatic polynomial.
I am going to introduce an advanced graph theory topic which is very much required for the computer science and the IT students. Yes, the topic is prefix code, which is also known as the prefix free code. But before starting this prefix code, we should know few definitions which already we know actually. So the first definition is a connected graph with no cycle is a tree. Hope everybody know this. And the second one is, in a tree, every vertex is an articulation point. We know if the structure is a tree, then its every point is an articulation point. And the third one is, a disconnected graph with no cycle is a forest. So what we mean by the forest? So these 3 definition for, if we take one example, suppose these are the few vertices we consider. So if we say this one is our graph, then this one definitely forming a forest, because all are disconnected and no cycles will be forming here. Now if we construct this one, these vertices, if we join in this way, suppose this is first joining, then another joining, suppose we just do in this way, then the third one we can take in this way, and one more joining we can do in this way. So just look, this one is a tree now, and here no cycles are forming, but before drawing this tree, this one is the forest, and each point, each internal nodes here are the articulation point. So these 3 definitions we should know. Now we come to the point prefix code. So at first, let us do the definition. What is prefix code? So a prefix code is a variable length code in which no code word is a prefix of another one. I hope you can't understand. Me too. So anyways, so let us explain this one with an example. So first of all, a prefix code means few variables are there, and for these variables we just set some prefix codes, and depending upon that we can draw a binary tree. But this prefix code are taken in such a way that no variable's prefix code is the prefix of some another variable's prefix code. So let us explain. First of all, these are the 4 variables. For these, if we want to draw a binary tree, then let us see how to draw. First, this one is the root vertex. This one is the root vertex. Now from here, we just take the 2 child vertices, because this one is a binary tree. So definitely we should get 2 child node from this root vertex. So this one we say it is the child node with the edge 0. That means as it is the binary tree, always 2 childs will be there. So these 2 childs we denoted by always 0 and 1. So the left side always be provided by 0 and the right side always denoted by 1. So if we do so, here the first code is A. So A means 0. So from the root, the left one, it is the 0. So we can say this node is the notation for the A. Next it is the B. B, its prefix code is 1, 0. So here from the root node, we always start from the root node. So root node from, it is 1 already we find out. So from here again we should get the 2 child node. So accordingly, if this one we shall go, then it is 1, then 0. So it is the B. Now the C variable, its prefix code is 1, 1, 0. So 1 is this one, and another one we shall find out this one. From here again, if our requirement is the 0, so from here we should get the 2 child node again. So this one is 0. So we say this one is our C variable. Now here D is 1, 1, 1. So definitely 1, 1, 1 means this node is denoted by D. So this one is our prefix code, and by a binary tree we can represent this prefix code for the given variables in this way. But the thing is, I am telling you here the 4 variables are given. These are its prefix code, and this is the binary tree. But how we can understand that these are actually the prefix code? What is the identification of it? So for that, with an example again, we are going to understand that the given prefix codes are actually a prefix code or not. So to verify that, here I am taking 2 examples. One set of variables is A, its prefix code is 0, B, its prefix code is 100, C, its prefix code is 101, and D, its prefix code is 11. This one is one set of variables, and another one is given as A, whose prefix code is 0, B, his prefix code is 01, C, its prefix code is 011, and D, its prefix code is 111. So depending upon these two, we should create our binary tree. So at first we should create, after that we analyze that what happened to these. So now for the first example, if we will start, then we find out for A, it is the root, and then from A as it is 0, so this one should be the A. Now B is 100. So for that, here this from root node, if we shall come out here, then it is 1. From here we should take the child node, because from there we find out the 0 node, that is this 0. Then after that, from here again we should take the 2 child nodes, so that we again get 0, and this point leads to the point B. Now C, its value is 101. So from root it is 1, then 0 means this one, and 1 means this one, so it is our C. Next it is D. D means it is 1, 1, so that from root node it is 1, and again this is 1, so we can say this node is D. And if the second example we consider, then from here we get this binary tree. A means this node, B means 0, 1, so 0 is this one, 1 is this one, so B node is this one. I hope you understand. Then C is 0, 1, 1, so 0, then 1, then 1. no, 0, then 1, then 1, this one. So this is our C node, and D node is 1, 1, 1. That means it is 1. From here it is again 1, and from here it is 1. So it is the D node. So in these two binary trees, if we will find out that in first binary tree, all the given variables lies in the leaf node, lies in the leaf node or the external node. But here few variables are internal node. Few variables are representing the internal nodes. So from the given prefix code, if you shall find out any binary tree where its nodes, that means its external nodes only representing the variable, then only we can say the given set of data is representing the prefix code. Otherwise it is not a prefix code. That means this first one is the example of prefix code, but the second one is not an example of prefix code. These are not the prefix code. From here, if we observe the data, then also we find out one variable representing by 0 and the another variable is 0, 1. So if we just forget about 1, then 0 is the representation which is already represented by A. So this type of prefix values are not allowed. If this type of things will be there, then these are not the prefix code representation. Now the purpose of this prefix code, we shall find out that what is prefix code, how to find out the prefix code, and using this prefix code how to draw the binary tree. But what is the purpose of this prefix code? What we should do by knowing this prefix code? So the main purpose of this prefix code is to encode or compress the data. One set of data is given. If we want to encode this data or compress, if we want to compress this data, then we require this prefix code. Basically in the security purpose or basically in the security purpose we require this one. So if we want to compress, then what happens? The best code will be the one with minimum possible length. So if we want to compress a data, then what should be the efficiently, we say what is the efficient coding by which we can encode or compress the data. So for that we should take the best code which will just create the minimum possible length of the given information. And not only that, to minimized average length, symbols with higher probability appearance will be assigned a shorter code than those with the lower probability. What does it mean? That means suppose a coded sequence is given, there whatever be the digits or numbers are given, so which numbers are appearing many number of times, these definitely have the higher probability to appear. So this type of data for we should use the short length for the prefix code, and which are occurring lesser time, that for we may consider the greater symbol for the prefix code. So with an example, or we just find out one application for this prefix code to understand it better. So let us do that. One statement is given, engineering decoding, and we want to encode this one using the prefix code. So what we will do first, whatever be the numbers are given, we should find out, here the characters are used. So each character we should find out that which are the different characters. So in this engineering decoding, here ENGIRDEEC, then O, these are the different characters which are used. E occurs 5 times, you just verify, E occurs 5 times, N 4 times, G 3 times, I 3 times, then R 1 times, D 2 times, C 1 times, and O 1 times. So these are the different characters and these are the corresponding frequencies. So now we can find out the corresponding probability by dividing this frequency with the total number of data. Here in engineering decoding, total 20 characters are used. So its corresponding probability we shall find out just by dividing each and every frequency by 20, and in fractional form we can write down in this way, so that these are the corresponding probability for the given data. So this is our basic structure which we should form by given any statement which we are supposed to compress or encode. Now what to do? We should form the binary tree so that we can give the prefix code to each and every character, because we want to replace each and every character by the prefix code. So how to do this one? What happened? So initially whatever be the different datas are there, that means different characters are there, we should write them in its ascending order of frequency or probability. Here I have used the frequency. So these are all the digits, all the characters which are used to form the word engineering decoding. Here the corresponding frequencies are written below. Now how to form the binary tree here? At first we should consider the lowest two frequencies. So here the lowest frequency is 1, 1, 1, 3. So among these three, any two we should consider. So using this any two, we should form the tree structure. So this one, and their total summation of frequency is what? 2. So that we should write here. Now among the remaining, that means this 2 should be included. Now this 2 and this remaining all, among all those, which are the two minimum values? So among these, the two minimum values are 1, 2, or it is the 2, 1, 2. These three, among these three we have to choose. So this one is fixed, and among these both two, any one we should select. So if we do so, then suppose we take 1 and 2, these two. So accordingly we just form, these are two child and their frequency total is 3. So now the frequency values appear 2, 3, 3, 3, 4 and 5. So among these all, which are the minimum frequency values? So that we can take here 2 and 3. So we can take these two and accordingly we combine these two. So if we combine these two, then we shall find out this is 5. Now what to do? Now we just combine these two, because now 3, 3, these are the minimum frequency values. So that now if we combine this, then we shall find out from here, and this value is 6. Next minimum values are what? Here the 4, 5, and here also 5 and 6. So among these we can say 4 and 5 are the less, so that we can create the another combination. So this is 4 plus 5, it is 9. So now our frequency values are 5, 6 and 9. So among these three, which two are minimum? This is 5 and 6. So definitely we should combine this 5 and 6. So if we combine, then we shall find out here the total sum is 11. Next it is the minimum 2, it is 11 and 9, and definitely we should just combine these two, so that we just have a look. So if we combine these two, we shall find out the total sum is 20. So that is the total frequency which we will find out. So in this way we just form the binary tree. Now binary tree formed. Now what we know, in binary tree left side is 0 and right side is 1. So accordingly whatever be the left side we shall find out, we should put it 0, and right side wing we should put at 1. So similarly here also it is 0 and 1, then it is 0, 1, 0, 1, 0, 1, and it is 0 and 1. So we just put the value for each wing. Now what we should find out from here, that the variables are these. So R, its prefix code should be then what? It should be then started from here, it is 0, 0, then 0 and 0. So R, its prefix code should be 0, 0, 0 and 0. Similarly for the C, its prefix code is what? It should be 0, 0, 0 and then 1. So it should be 0, 0, 0 and 1. Now O, its prefix code should be what? It's always we should start from the root. So it is 0, then again 0, after that it is 1, and then it is 0. So that it is 0, 0, 1 and 0. Now for D similarly we should find out 0, 0, 1 and 1. So it is 0, then 0, 1, 1. Now for G it should be 0, then it is 1, then it is 0. So it is 0, 1, 0, and for I similarly it is 0, 1, 1, and for N it is 1, directly 1 and 0. So it is 1 and 0, and for E it is 1 and 1. So just look, we shall find out the prefix code for all those datas. Here you just verify one thing, that these are all different values or characters. Each different values have the different frequencies. Among these, E, this character have the highest frequency, which is 5. And R, C and O, these have the lowest frequency, these are 1, 1, 1. So depending upon the frequency, we shall find out that the number of prefix codes are higher or lower. As the lower frequency values are here, so that 4 digits we use as the prefix code. As here the higher frequency is given, so we use lesser prefix code. What happens by this? Because when E repeated more number of times, we use only 2 prefix code. Only 2 prefix code means we allocate the less memory. And as E occurs much frequently than the other characters, that's why the memory allocation by using only 2 prefix code will be lesser. So in this way we can do the memory allocation minimize by taking this prefix code, and in this way we just set the prefix code by taking the weighted binary tree. In this way we just draw the binary tree. I hope you understand how to draw the binary tree. I am just repeating the statement again. Just rearrange the characters by its corresponding frequencies, and after that you just collect at a time 2 lowest frequencies and merge them. After that, from the new set of data, you again find out 2 minimum frequencies and then merge them. If you have a tie, then you can choose any one of them. So in this way we can create the binary tree, and we just set the prefix code. So after this prefix code we just make a table. So in this table these are the different characters, these are their corresponding frequencies, and these are their prefix codes. So using this one, what we can just encode the given statement engineering decoding, that is definitely in this way we should send the data. So here the first one representing the E, I hope you understand. The second one is N, so N value is 10, so this one, so we just write the sequence of these 10 values, and we, instead of engineering decoding, we can write this sequence. And for the memory allocation, we know that if the engineering decoding we use as it is, then there are total 80 characters, and each characters required 8 bit in computers. That's why total 160 bit it required to write. And if we use the prefix code, then if we count all these numbers, then we find out it is 56 in numbers. So in this way we can just minimize the memory allocation. So this is the way by which we can use the prefix code, and this method of using is called also the Hoffman coding. So this one is for the binary tree, but not always necessary that using the binary tree we just get the prefix code, or we just apply the prefix code for binary tree also only. But if there are n-ary tree, then also we can apply the prefix code. And if we use the higher binary tree, that means higher wing binary tree, if suppose it is 3-array binary tree, 4-array binary tree, so for those the memory allocation will be much more minimized. So just I am giving you for the 3-array tree so that you can understand how we just fit this prefix code to the higher order trees. So just have a look. Prefix code can be extended from binary tree to m-array tree by the following steps. So what is the step to extend it to the higher order trees? That is, first step, we should choose 1 plus n minus 1 mod of m minus 1 number of lowest value nodes. Look, at first we have the different characters or datas. So for those datas we have the different frequencies. After that we just arrange them in the ascending order of frequencies. After doing all those, we come to know that how many total different digits or characters we have. And if we are supposed to make it m array, that means there are, for the root, m number of childs are there. So if we will want to do so, then this n minus 1 mod m minus 1, n is the total number of characters, different characters, and m is the how many childs we want to form for a binary tree. If it is 3 array, then its value is 3. If it is 4 array, then it is 4, and if it is m array, then it is m. So with this one we add 1 and calculate this one. I hope you understand that n minus 1 mod m minus 1 means what? This is the remainder if we divide n minus 1 by m minus 1. So that remainder value gives us this value plus 1. Whatever be the value you shall find out, initial choice for, we should consider that number of nodes. After taking that number of nodes, for the next subsequent steps, we choose m array number of combinations. That means if it is 3 array, then 3 nodes in the next step form and onwards we should choose. So if we do with an example, I am just giving you the example for this one also. Here I am taking the same example as the binary tree for I have taken. Here if I have this n minus 1 mod of m minus 1, then just have a look. Here total number of variables are 8, that means different characters are 8. So it is 8 minus 1, then it is mod of 3 minus 1, because we are going to make it 3 array. So now this one means 7 mod of 2. So its remainder is 1. Now its remainder is 1, so that the formula is 1 plus of this one. So that 1 plus this one means total 2. So initially we have start from the 2 nodes. So here 2 nodes with the minimum frequency value, let us consider these 2. So accordingly we just form this one. So its total value is 2. This 1 plus 1 is 2. Now onwards we should consider 3 at a time. So when we are going to consider 3 at a time, then we should consider 2, 1, 2 in the first step, because these are the lowest value frequencies. So if we just add them, then we shall find out this way. So this one. So total value is what? 2 plus 1 plus 2. That means it is 5. Now after doing this one, now the minimum 3 more. So minimum 3, which 3 we should consider? 3, 3, 4 definitely we should consider, because these 3 are the lowest. So if we take this one, then we shall find out this, and its total valuation is 10. I think 4 plus 3 7 plus 3 10. Now the 3 nodes are left, 5, 5 and 10. So we have to merge these 3. Just have a look. And the total value is 20. So if we consider the trinary tree, then this way we can form the prefix code, and here the age value we should write, as the 3 edges are there. So it is 0, 1 and 2 we should consider. Here also we consider 0, 1 and 2. This one is 0, 1 and 2, and here 0 and 1. So in this way we just put the values, and depending on these values we should substitute the prefix code value. So for R the prefix code is 0, 0, 0. For C it is 0, 0, 1. For O it is 0 and 1. For D it is 0 and 2. For G it is 1, 0. Here it is for I 1, 1. For N it is 1, 2. And for E it is only 2. So these are the corresponding prefix codes for these given characters, and on that basis we just find out that each character for the number of allocations of the prefix codes are here 3, 3, 2, 2, 2, 2, 2 and 1. So definitely more less memory, that means here we just use the much lesser memory allocation than the binary tree consideration while we take the prefix code. So in this way the prefix code can be used, and we can just encode any statement is given, and we can send it to anyone for the security purpose or the privacy. So this is our prefix code. I hope you understand, and have a nice day. Thank you all.